Have you ever looked at your own hand and really asked yourself what it is? I do not mean the skin or the muscles or the bones that structure your fingers. I mean the stuff itself, the matter. If you press your hand against a table, it feels solid. It feels like there is no space between you and the wood. It feels like a continuous, unbroken reality. But this is the first and greatest lie that the universe tells us. The reality, the honest truth that physics reveals to us, is that you are almost entirely made of nothing. If we were to look deep inside the atoms that make up your body, past the cells, past the molecules, down to the subatomic level, we would find a disturbing amount of emptiness. Picture a large football stadium. Imagine that the nucleus of an atom, the heavy center where almost all the mass lives, is a marble sitting on the 50-yard line. The electrons? They are tiny specks of dust whizzing around the very top rows of the bleachers. Everything in between, the field, the lower stands, the air inside that stadium, is just empty space. It is a void. And yet, you feel solid, you feel heavy. That sensation of touch, of resistance, is just electromagnetic forces repelling each other like magnets refusing to touch. It is a ghost pushing against a ghost. But what if we could turn off that force? What if we could break the rules that keep that stadium empty? What if we could take all the humanity on Earth, every single one of the 8 billion people living, breathing, and dreaming right now, and remove that empty space? If we squeezed all of us down to just our nuclei, removing the void inside our atoms, the entire human race would fit inside a volume the size of a sugar cube. Think about that. All our history, all our wars, all our love compressed into a sugar cube. That concept seems impossible. It seems like a mathematical game, a fantasy that has no place in the real world. But the universe is far more creative and far more terrifying than our imaginations can grasp. There is a place where this nightmare of density is real. There is a place where the emptiness is crushed out of existence, leaving behind something so heavy, so dense, and so extreme that it breaks our understanding of what matter can be. This place is not a black hole which hides its secrets behind an event horizon. It is a star, a dead star, a city-sized sphere of matter that weighs more than our sun. It is the neutron star. And today, we are going to peel back the layers of this cosmic monster to understand what it is truly made of. Hello, my friends. I am Theodore, the researcher. If you enjoy these quiet journeys into the deepest mysteries of the cosmos, if you find peace in understanding the scale of the universe, and if you want to support this channel as we translate the incomprehensible into the understandable, please take a moment right now to subscribe. It is a small click for you, but it means the world to us. It allows us to keep exploring, keep questioning, and keep wondering together. Thank you. Now, let us return to the darkness. To understand what a neutron star is made of, we first have to understand how the universe manufactures such an object. You cannot build one in a laboratory. You cannot find one growing in a nebula. A neutron star is a tombstone. It is what remains after a violent, catastrophic death. Imagine a star much massive than our sun, perhaps 10 or 20 times more massive. For millions of years, this star has been a battlefield. 2 great forces have been locked in a war for survival. Gravity, the crushing weight of the star's own mass, wants to pull everything inward, to collapse the star into a single point. Opposing it is the pressure generated by nuclear fusion in the core. The star burns hydrogen into helium, releasing energy that pushes outward, holding gravity at bay. It is a delicate balance, a stalemate that lasts for eons. But the star is running out of fuel. It burns helium into carbon into neon, then oxygen, then silicon. Each stage happens faster than the last. The star is desperate. It is burning through its reserves, trying to generate enough heat to stop the crushing hand of gravity. But eventually it reaches the end of the line. It starts creating iron in its core. Iron is the poison of stars. Fusing iron does not release energy. It consumes it. The moment iron appears, the war is lost. The outward pressure stops. The balance is broken. In a fraction of a second, less time than it takes you to blink, gravity wins. The core of the star, an object roughly the size of Earth, collapses inward at about 25% of the speed of light. This collapse is the most violent event in the universe since the Big Bang. The outer layers of the star are blown apart in a supernova explosion, a blast so bright it can outshine an entire galaxy of billions of stars. But we are not looking at the explosion. We are looking at what is happening in the center. We are looking at the core. As it collapses, the pressure becomes so intense that the laws of atomic physics are shattered. Remember the stadium analogy? Remember the empty space between the marble and the bleachers. Gravity is now crushing the stadium. The electrons, those tiny specks of dust, are being squeezed inward. They have nowhere to go. They are pushed into the nucleus. They are forced to merge with the protons. When a negative electron merges with a positive proton, they cancel each other out. They become a neutron. This is a fundamental transformation of matter. The electric charges are gone. The repulsion that kept the atoms empty is gone. The stadium is gone. The entire core of the star, once the size of a planet, is crushed down into a sphere only about 20 kilometers or 12 miles across. It is the size of a city like London or Manhattan, but it still contains the mass of 500,000 Earths. Let us pause here and try to visualize this. It is easy to say 20 kilometers wide and mass of the sun, but those are just words. We need to feel the weight of this. Imagine you have a teaspoon, a simple silver teaspoon, from your kitchen drawer. Now, imagine we could fly to this neutron star, survive the radiation, land on its surface, and scoop up just 1 teaspoon of this material. How much would it weigh? On Earth, a teaspoon of water weighs about 5 grams. A teaspoon of lead, which we think of as heavy, weighs about 60 grams. A teaspoon of gold weighs about 100 grams. But a teaspoon of neutron star matter, it would weigh roughly 1 billion tons. 1 billion tons. That is not just a heavy rock. That is the weight of Mount Everest. That is the weight of every single car, truck, and bus in the United States. Combined, crushed into a spoon. If you were to drop that teaspoon on Earth, it would not just sit on the table. It would fall through the table. It would fall through the floor. It would punch through the concrete foundation of your house. It would slice through the Earth's crust and mantle like a steel ball falling through mist. It would fall all the way to the center of our planet, driven by its own incredible density. This is the reality of the neutron star. It is an object where the concept of empty space has been erased. It is the most dense object in the universe that still has a surface. Black holes are denser, yes, but they are singularities, points of infinite density where physics breaks down. A neutron star is real matter. You can touch it, technically. It has a crust. It has a landscape. It has mountains, though they are only millimeters high. Because the gravity on the surface is so intense, nothing can stand tall. If you were to stand on the surface of a neutron star, assuming you were indestructible, you would be flattened into a layer of atoms, one thicker than a sheet of paper, instantly. The gravity there is 100 billion times stronger than on Earth. To escape the gravity of Earth, a rocket needs to travel at 11 kilometers per second. To escape the gravity of a neutron star, you would need to travel at 100,000 kilometers per second. That is 1/3 the speed of light. If you dropped an object from just 1 meter above the surface, it would hit the ground in a microsecond, moving at millions of kilometers per hour. The impact would release more energy than a nuclear warhead, and yet, despite this violence, despite this terrifying hostility, the neutron star is a quiet thing. It spins in the darkness, a dead ember of a once glorious sun. It is a sphere of perfect geometry, smoother than any billiard ball humanity has ever machined. The variations in its height are measured in atomic widths. It is a jewel of compressed reality. But what is happening inside? If we could slice this city-sized atomic nucleus open, what would we see? Is it just neutrons all the way down? Is it a solid block of neutral particles? The answer, as we are discovering, is far more complex and beautiful. The interior of a neutron star is not just a uniform soup. It has structure. It has geology. It has phases of matter that exist nowhere else in the universe. It is a laboratory where nature tests the absolute limits of physics. As we journey from the surface down to the core, we will encounter matter that behaves like a solid, matter that behaves like a liquid, and matter that behaves like nothing we have a name for. We will find layers that scientists have whimsically named after pasta, spaghetti, lasagna, gnocchi, because of the shapes the nuclei are forced into. We will find fluids that flow without friction, spinning forever without losing energy. We might even find the breaking point of the neutron itself, where the basic building blocks of matter dissolve into a primordial soup of quarks. This is the journey we are about to take. We are going to descend into the most hostile environment in the cosmos. We are going to look at the star stuff that Carl Sagan famously spoke of, but in its most extreme form. We are familiar with the star stuff that makes us, the carbon in our DNA, the calcium in our teeth. That is fluffy, low-density star stuff. That is the foam on top of the ocean. The neutron star is the ocean floor. It is the deep, crushing truth of what matter can become when the universe stops being polite. It forces us to ask a profound question. If this is what matter can be, then what are we? If the natural state of matter under gravity is this hyperdense crystal of neutrons, then our existence as low-density, water-filled biological machines is a rare and fragile exception. We are the anomaly. The neutron star is the rule. So let us prepare our minds for this descent. We will start at the atmosphere. Yes, these dead stars have atmospheres. And we will dig down through the crust, through the pasta phases, into the superfluid ocean of the outer core, and finally, into the great unknown of the inner core. Each layer tells a story. Each layer reveals a different aspect of the strong nuclear force, the force that binds the universe together. It is a journey from the known into the unknown, from the physics of the classroom into the physics of the impossible. And it begins with a thin, hot layer of carbon floating on top of a diamond ocean. Consider for a moment the silence of space around this object. It is a silence that hides the most extreme magnetic fields in the universe. Some neutron stars, called Magnetars, have magnetic fields 1 trillion times stronger than Earth's. If a magnetar were to fly past the moon, halfway between Earth and the moon, its magnetic field would be strong enough to wipe every credit card on Earth. It would be strong enough to rip the iron out of your blood. This is the environment we are approaching. It is a place where energy and matter are twisted into forms that defy our daily intuition. But we have mathematics. We have observation. We have the human capacity to imagine. And with these tools, we can touch the surface of the nightmare. As we approach the star in our imagination, the first thing we notice is the light. It is not like the sun. It does not shine with a yellow warmth. It glows with a terrifying X-ray intensity. The surface temperature is millions of degrees. It is a small, blinding point of light, no bigger than a city, yet pulsing with the energy of a sun. It spins rapidly, perhaps hundreds of times every second, a lighthouse beam sweeping across the cosmos. This is the pulsar, but we are going closer. We are going past the beams. We are going to land on the impossible. The journey into the neutron star is a journey into the heart of density itself. It is a reminder that our perception of the world is limited by our biology. We evolved to understand rocks and water and air. We did not evolve to understand degenerate matter. We did not evolve to understand the quantum mechanics of the very large. But we can learn. We can stretch our minds, and in doing so, we connect ourselves to the grandest scales of reality. We stop being just observers and become participants in the cosmic story. So, take a deep breath. Let go of your intuition about what is solid and what is empty. Let go of your understanding of heavy and light. Those concepts do not apply here. Here, there is only the crush. Here, there is only the neutron. We are now hovering just above the surface of the beast. In our imagination, we are protected from the forces that would instantly obliterate biological matter, but we must respect them. The first thing that assaults your senses is the distortion of space itself. Because the gravity here is so intense, it bends light paths into circles. If you were to look out toward the horizon, you would not see a flat line or a gentle curve like on Earth. You would see the horizon curving upward as if you were sitting at the bottom of a great bowl. And, stranger still, if you looked closely at the edges of the star, you would see something that defies logic. You would see the back of the star. The gravity is so powerful that it pulls photons from the far side of the sphere, bends them around the curvature, and sends them straight into your eyes. You can see more than half of the star at once. It is a geometry of madness, a place where Euclid's rules have been twisted by the sheer weight of mass. Beneath us lies the atmosphere, When we say atmosphere on Earth, we think of kilometers of blue sky, towering clouds, the breathable mix of nitrogen and oxygen that shields us from the vacuum. Here, the atmosphere is a mockery of that concept. It is incredibly thin. If you were standing on the solid surface, the sky would not extend for kilometers. It would extend for perhaps a few centimeters, maybe a meter at most. That is it. The entire gaseous envelope of the star is compressed by gravity into a layer thinner than the mist on a morning pond. And it is not made of air. It is a plasma of hot carbon, perhaps some helium, superheated to millions of degrees Celsius. It is heavy, dense, and lethal. The pressure at the bottom of this 1-meter atmosphere is higher than the pressure at the bottom of Earth's deepest ocean trenches. It is a crushing blanket of fire that marks the boundary between the void of space and the hard reality of the star. If you are just joining us on this descent into the impossible, I am Theodore, the researcher. We are currently exploring the most extreme object in the universe, layer by layer. If this kind of deep-dive scientific storytelling resonates with you, and if you want to ensure you do not miss the journey into the core that is coming next, please verify that you are subscribed to the channel. It is the best way to support this work. Now, let us touch the surface. Beneath that thin, blazing atmosphere lies the crust. This is where the neutron star becomes truly alien. On Earth, the crust is made of rock, silicates, granites, basalts. It is rigid, but on a planetary scale, it is flexible. Tectonic plates move, continents drift. Here, the crust is a lattice of iron. Remember the death of the progenitor star? It died because it made iron. That iron is still here, but it has been transformed. The gravity and pressure have squeezed the iron atoms so close together that they form a perfect crystal lattice. It is a solid ocean of iron nuclei, locked in place, unable to move. But these are not normal atoms. On Earth, atoms are surrounded by clouds of electrons. Here, the pressure is so high that the electron clouds have been crushed. The electrons have been ripped away from their nuclei. They are no longer bound to specific parents. Instead, they form a degenerate gas, a quantum sea of electrons that flows freely through the iron lattice. This makes the crust of a neutron star one of the most electrically conductive materials in the universe. It conducts electricity better than copper, better than gold, better than any superconductor we have ever created. And it is hard. The word hard does not do it justice. Steel is hard. Diamond is hard. The crust of a neutron star is 10 billion times stronger than steel. It is the strongest material in the known universe. If you were to strike it with a hammer, assuming you could lift the hammer against the gravity, the hammer would shatter, the atoms of the hammer would fuse, and the crust would not even scratch. It is a rigid, unyielding shell that locks the star's secrets inside. This extreme rigidity creates a fascinating and terrifying possibility. Because the star is spinning so fast, hundreds of times per second, it wants to flatten out. It wants to be an oblate spheroid, like a squashed ball. But as the star slows down over millions of years, gravity tries to pull it back into a perfect sphere. On Earth, the crust shifts slowly, causing earthquakes. On a neutron star, the crust cannot shift slowly. It is too stiff. It holds the tension, building up stress for years, decades, centuries. the strain becomes unbearable. The iron lattice creates a tension that exceeds the binding energy of normal matter, and then, in a microsecond, it snaps. The crust cracks. This is a starquake. On Earth, a big earthquake might move the ground a few meters and release enough energy to destroy a city. On a neutron star, the crust moves only a fraction of a millimeter, perhaps the width of a single atom. But because the material is so dense and the gravity so high, that tiny movement releases an apocalyptic amount of energy. A starquake can release more energy in 1 second than our sun releases in 100,000 years. The crack in the crust sends shock waves through the star, and it shakes the magnetic field lines rooted in the surface. This magnetic shake accelerates particles to nearly the speed of light, blasting out a flash of gamma rays that can blind satellites across the galaxy. We have detected these events. We call them soft gamma repeaters. For a brief moment, a single neutron star becomes the brightest object in the sky, all because its skin shifted by a millimeter. It is a reminder that in this domain, the smallest movements carry the greatest consequences. But we are not stopping at the surface. We must go deeper. We must push through this iron crust and descend toward the interior. As we dig down, metaphorically of course, since digging here is impossible, the density begins to climb even higher. We are now a few hundred meters below the surface. The weight of the material above us is crushing the nuclei together. The iron nuclei are getting uncomfortable. They are being forced into proximity that they hate. Nature has a rule. Protons repel protons. They are both positively charged, and they want to be apart. But gravity is forcing them into a crowded elevator. To survive this pressure, the nuclei begin to change. They start to absorb the electrons swimming around them. This is a process called electron capture. A proton eats an electron and becomes a neutron. The nuclei are becoming neutron-rich. They are evolving from iron into heavier, more exotic isotopes, elements that are unstable on Earth and would instantly radioactive decay. But here, under the crushing weight, they are stable. We are seeing isotopes of nickel, krypton, and heavier elements that have bloated with extra neutrons. The deeper we go, the more neutrons are stuffed into the nuclei. It is as if the star is trying to turn everything into neutrons, but the crystal lattice is fighting to maintain its structure. It is a battle between the desire for order and the desire for collapse. This region is known as the inner crust. Here, the physics becomes slippery. The nuclei are so bloated with neutrons that they can no longer hold them all. Imagine a sponge that is so soaked with water that it starts to drip. This is exactly what happens here. We reach a depth, perhaps half a kilometer down, where we hit the neutron drip point. This is a critical boundary in the geography of the star. Above this point, neutrons are locked inside the nuclei. Below this point, the neutrons start to leak out. They drip out of the atomic lattice and form a free ocean of superfluid neutrons. It is a state of matter that defies common sense. You still have the solid crystal lattice of heavy nuclei, the solid part, but flowing through it, around it, and inside it is a liquid of pure neutrons that has zero viscosity. Friction does not exist here. If you stirred this neutron soup, it would spin forever. It is a superfluid. This mixture of solid crystal and frictionless liquid is unlike anything in our human experience. It is a quantum hybrid, and it is here that the star begins to hide its true strangeness. The deeper we go into the inner crust, the stranger the shapes become. We are now approaching the boundary between the crust and the core. The pressure is rising to 10 trillion times the density of lead. The nuclei, those bloated spheres of neutrons and protons, are being pushed so close together that they start to touch. They can no longer maintain their spherical shapes. They start to deform. They merge and stretch. This is where the scientists, in a moment of delightful humanity, turn to the kitchen for terminology. We call this region the nuclear pasta phase. It is not a joke. It is the actual scientific term used in serious astrophysics papers. As the nuclei get squeezed, they first stretch out into long cylinders. We call this spaghetti phase. Millions of tons of nuclear matter stretched into long, thin strands. Go deeper, and the cylinders get pressed into flat sheets. We call this lasagna phase. Sheets of nuclear matter stacked on top of each other, separated by the superfluid neutron sauce. Go deeper still, and the sheets merge, leaving only tubes of empty space, the anti-spaghetti. And finally, just before the core, we hit the Swiss cheese phase, where it is solid nuclear matter with just a few holes of vacuum left. This nuclear pasta is the strongest material in the universe. It is stiff, resilient, and incredibly complex. It acts as the final barrier, the last stand of structure, before everything dissolves into the uniform soup of the core. It represents the absolute limit of what we can call shape. Below the pasta, there are no shapes. There are no cylinders, no sheets, no spheres. There is only the liquid. But the pasta phase is crucial. It might be responsible for the way neutron stars spin, the way they cool, and the way they emit gravitational waves. It is a layer of hidden complexity, a secret architectural masterpiece buried under a mountain of iron. It forces us to realize that the universe is an artist even in the dark. It sculpts matter into geometry, even when there is no one there to see it. It creates order under the most horrific pressure. As we pass through the lasagna and the Swiss cheese, the holes begin to close. The voids disappear. The last remnants of empty space are squeezed out. The distinction between nuclei and free neutrons vanishes. The crystal lattice dissolves. We've reached the bottom of the crust. We're about 1 or 2 kilometers deep. Above us is the weight of a sun. Below us is the core. We have left the realm of solid matter behind. We are entering the quantum ocean. Here, the density reaches the density of the atomic nucleus itself. The entire star, at this depth, is effectively one single giant nucleus. It is here that the true mystery begins. What happens when you squeeze neutrons until they touch? Do they stay as neutrons? Or do they break down? Do they turn into something else? This is the frontier of modern physics. This is the edge of the map. But before we dive into that liquid abyss, let us pause and look back up at the crust we just traversed. Think about the stability of it. This star has been dead for millions of years, yet it maintains this perfect, rigid structure. It is a monument to the laws of quantum mechanics. On Earth, everything decays. Mountains erode, buildings crumble, biological bodies rot. Entropy destroys all structure. But the neutron star is different. It is locked in a quantum stalemate. It cannot crumble because there is no space to crumble into. It cannot erode because gravity holds it in a vice grip. It is, in a strange way, eternal, unless it feeds, unless it collides. Left alone, the neutron star is a diamond in the dark, preserving its structure against the end of time. It is a reminder that dead does not mean chaos. In the cosmos, death can bring a stillness and a perfection that life can never achieve. We, with our fluid bodies and changing minds, are defined by our instability. We flow, we change, we die. The neutron star simply is. It is the ultimate stoic of the universe, enduring pressures that would erase a solar system, and doing so with a surface that is polished to the atom. Now, we must prepare ourselves for the transition. We are leaving the world of shapes, the lattice, the pasta, the crust. We are entering the world of fluids. But this is not water. It is a fluid of particles that occupy the same quantum state, moving in unison, a chorus of matter singing the same note. We are entering the outer core. This is where the magnetic fields are born. This is where the star stores its heat. This is where the ghosts of the protons and neutrons swim in a soup that is denser than imagination. It is a place where the rules of the macroscopic world, friction, viscosity, resistance, simply vanish. It is a world of magic, powered by the strong force. We are about to dissolve into the soup. The boundary is crossed. We have left the solid world behind. We are now submerging into the outer core of the neutron star. If you thought the crust was strange, with its crystal iron and nuclear pasta, the core is where the universe truly takes off its mask and reveals the quantum machinery underneath. Here, the density has climbed to roughly twice the density of an atomic nucleus. The matter around us is no longer arranged in a lattice. There are no shapes here. There is only a soup. But this is not a chaotic, boiling soup like the center of a normal star. It is a cold, ordered, and silent ocean. This is a liquid of pure neutrons, mixed with a sprinkling of protons and electrons. But because of the extreme pressure and the quantum laws that govern this realm, this liquid behaves like nothing you have ever seen. It is a superfluid. On Earth, if you stir a cup of coffee and then stop, the coffee eventually stops spinning. Friction between the liquid and the cup, and friction within the liquid itself, drains the energy. The swirl dies down. In the outer core of a neutron star, friction has been outlawed. The neutrons have paired up, forming what physicists call Cooper pairs, and they have entered a quantum state where they flow with absolutely zero resistance. If you could stir this neutron ocean, it would spin forever. It would never lose energy. It would never slow down. It is a perpetual motion machine of nature's own making, powered by the laws of the strong nuclear interaction. This superfluidity changes everything about how the star behaves. It means the core does not rotate like a solid ball. It rotates like a quantum bucket. It forms tiny, invisible tornadoes called quantized vortices. Imagine billions of microscopic whirlpools, each one carrying a specific unit of rotation threading through the star from pole to pole. The star's rotation is not a smooth motion. It is the sum of these billions of tiny storms. But there is a complication. Remember the protons? There are not many of them here, perhaps only a few % of the mixture, but they are crucial. They too have paired up. They too have condensed into a quantum state. But because protons carry an electric charge, they do not become superfluids. They become superconductors. A superconductor is a material that conducts electricity with zero resistance. On Earth, we have to cool materials to near absolute zero to achieve this. In the heart of a neutron star, at temperatures of millions of degrees, superconductivity is the natural state. This proton superconductor locks in the star's magnetic field. The magnetic field lines cannot move through the superconductor. They are pinned in place. This is why neutron stars have such stable and terrifyingly strong magnetic fields. The magnetism is frozen into the star, trapped by the superconducting protons, anchored for eternity. And here lies the source of a cosmic glitch. The neutron star is spinning. The crust is solid and spins at one speed. The superfluid core is liquid and spins independently. As the star ages, it emits radiation and slowly loses energy. The crust slows down. But the superfluid core, it has no friction. It does not want to slow down. It keeps spinning fast, carrying the memory of the star's youth. A tension builds. The superfluid vortices in the core are pinned to the inner crust, grabbing onto the nuclear pasta we saw earlier. They want to keep the crust moving fast. The crust wants to slow down. The stress builds for years, decades, and then, snap, the vortices unpin. In a catastrophic release, the superfluid core transfers a massive kick of angular momentum to the crust. The entire star suddenly speeds up. It is a glitch. Astronomers watching from Earth see the pulsar suddenly change its rhythm. For a brief moment, the star defies the breaking power of the universe and accelerates, driven by the frictionless engine hidden in its belly. It is the heartbeat of a quantum monster, a stutter in the spin that tells us the liquid inside is real. I am Theodore, the researcher, and we are currently swimming through the most hostile ocean in existence. If you are finding value in this deep exploration of the cosmos, if you appreciate the effort to visualize the invisible, please verify that you are subscribed to the channel. Your presence here helps us continue these broadcasts from the edge of knowledge. Now, we must go deeper. We are descending past the outer core. The density is rising. It is now 3 times, 4 times, 5 times the density of an atomic nucleus. The neutrons are being squeezed so tightly that they are overlapping. They are losing their individuality. We are entering the inner core. This is the terra incognita of astrophysics, the unknown land. We have theories about what happens here, but we have no proof. We cannot replicate these pressures on Earth. We can only listen to the faint signals of gravitational waves and look at the mass of the stars to guess what lies in the center. What happens when you crush a neutron? A neutron is not a fundamental particle. It is a bag made of 3 smaller particles called quarks. Specifically, 2 down quarks and 1 up quark, held together by gluons. Under normal conditions, the quarks are happy to stay inside their bag. They run around, confined by the strong force. But the pressure here is trying to crush the bag. The neutrons are packed so tight that the bags are grinding against each other. One possibility, one terrifying possibility, is that the neutrons break, the bags rip open, the boundaries dissolve. The matter stops being neutrons and becomes a continuous soup of free quarks. This is called quark matter. In this state, the quarks are free to roam the entire core. It is a sea of fundamental particles, a quark-gluon plasma similar to the state of the universe just microseconds after the Big Bang. But it is cold, relatively speaking, and stable. If this happens, the star is no longer a neutron star. It is a quark star, a hybrid object with neutron mantle and a quark heart. But the universe might be even stranger than that. As the pressure rises, the energy of the particles becomes so high that nature might decide to create new types of matter. We know of up and down quarks, but there is a heavier, more exotic cousin called the strange quark. Strange quarks are usually unstable. They decay quickly in our low-energy world. But under the crushing weight of the inner core, strange quarks might become stable. The high pressure might force some of the up and down quarks to convert into strange quarks. This would create a new kind of matter called strange matter. This is where the story turns into a cosmic horror movie. There is a hypothesis in physics called the strange matter hypothesis. It suggests that strange matter, this mixture of up, down, and strange quarks, is actually the true ground state of matter. It is more stable than iron. It is more stable than neutrons. It is the most perfect, most energy-efficient form of matter in the universe. Why is this scary? Because if strange matter is the most stable form of matter, then ordinary matter, the atoms in your body, the earth, the sun, is metastable. We are just waiting to be converted. If a droplet of strange matter, a strangelet, were to escape the core of a neutron star and touch a normal nucleus, it would instantly convert that nucleus into strange matter. It would release energy, which would convert the next nucleus and the next. A chain reaction would begin. If a single strangelet touched Earth, it could theoretically convert the entire planet into a hot ball of strange matter, roughly the size of a stadium. This is the Ice 9 scenario of astrophysics. Fortunately, strange matter is likely locked deep inside the gravity well of the neutron star. It cannot escape. But its presence in the core would change the star. Strange matter is squishier than neutron matter. It is more compressible. If the core turns into strange matter, the star can shrink even further. It becomes smaller, denser, more compact. A star made of strange matter might be only 10 kilometers across instead of 20. We look for these tiny stars. We hunt for them. If we find a neutron star that is too small to be made of neutrons, we will have found evidence that the center of these dead suns is a factory for the ultimate form of matter. Or perhaps the core goes in a different direction. Perhaps the pressure creates hyperons. These are heavy particles, cousins of the neutron, that contain strange quarks, but remain distinct particles. They are like neutrons on steroids. If they appear, they soften the core, making it harder for the star to support its own weight. This leads to a paradox. If hyperons form, the star should collapse into a black hole sooner. But we see massive neutron stars 2 times the mass of the Sun that haven't collapsed. This hyperon puzzle keeps physicists awake at night. It suggests that something is preventing the hyperons from forming, or that there is a force we do not understand pushing back against gravity. Maybe the quarks interact in ways we haven't modeled. Maybe the repulsive force of the strong interaction changes character at extreme densities. We are looking at a tug-of-war between the fundamental nature of particles and the crushing hand of gravity, and we do not know who wins in the final kilometer. Let us pause and consider the scale of what we are discussing. We are talking about a region of space no larger than a city park, the very center of the star, containing the mass of hundreds of millions of planets. In this tiny volume, the concepts of chemistry, biology, and even atomic physics are meaningless. There are no atoms. There are no molecules. There are no reactions. There is only the raw, naked substance of existence. If you could take a sample of the inner core, just a pinhead's worth, and teleport it to Earth, the release of confinement pressure would cause it to explode with the force of a large asteroid impact. The matter itself is a bomb, held together only by the gravity of the star. It is a prisoner, and this brings us to the edge of the ultimate precipice. What lies beyond the neutron star? We have been exploring the edge of the cliff. The neutron star is the last stop before reality breaks. If you add just a little more mass, perhaps dropping a few asteroids onto the surface or merging with another star, the pressure in the core becomes too great. The neutrons or the quarks or the strange matter, whatever is down there, can no longer fight back. The strong nuclear force, the strongest force in the universe, snaps. Gravity wins its final victory. The core collapses. The horizon closes. The star vanishes from the observable universe and becomes a black hole. The neutron star is the guardian of that boundary. It is the hardest object that can exist. It is the universe saying, this far and no further. It is the line in the sand. But what if the line is blurry? What if there are objects that straddle the boundary? We have begun to find them. The black widow pulsars eating their companions and growing massive. The collisions of neutron stars that send ripples through space-time. These events give us fleeting glimpses into the core. When two neutron stars crash for a fraction of a second, the temperature rises to trillions of degrees. The density spikes. We see the equation of state, the mathematical description of the matter, reveal itself in the gravitational waves. We are listening to the sound of the dense matter squishing. We are hearing the thud of the collision, and the tone of that thud tells us if the core is hard or soft, if it is neutrons or quarks. We are decoding the interior of the most impenetrable objects in the cosmos by listening to their death screams. This journey into the core of a neutron star is not just a tour of a distant object. It is a tour of the fundamental possibilities of our universe. We are made of up and down quarks, locked in protons and neutrons, surrounded by electrons. That is the standard recipe. But the neutron star shows us that the recipe can change. You can strip the electrons. You can crush the empty space. You can melt the protons. You can liberate the quarks. You can transmute the matter into something stranger. It shows us that solid, liquid, and gas are just local customs, provincial ideas that apply to our low-energy neighborhood. In the grand centers of power in the cosmos, matter is a fluid of quantum particles, superconducting, superfluid, strange, and terrifyingly heavy. So, when you look at the iron in your blood, remember where it came from. It was forged in a star. But also remember what it could become. If that iron were compressed, if it were subjected to the ultimate test, it would become the crystal crust of a neutron star. It would become the gatekeeper to the quark ocean. We are potential neutron stars waiting for gravity. The matter is the same. The difference is only space. The difference is only the void that keeps us fluffy and alive. We are walking ghosts, mostly empty space, pretending to be solid. The neutron star is the honest truth. It is the solid thing, and perhaps, in a universe of vast emptiness, there is something comforting about knowing that somewhere, in the dark, there is something that is truly, undeniably, unbrokenly real. Now that we have reached the center, we must ask, what happens when two of these monsters meet? What happens when the unstoppable force meets the immovable object? The universe has an answer, and it is written in gold. Literally. The gold in your wedding ring, the platinum in your catalytic converter, the uranium in our power plants. They were not born in normal stars. They were born in the fire of a neutron-star collision. We have explored the static star. Now we must explore the dynamic violence of the Kilonova. We must understand how the death of these dead stars gives life to the heavy elements of the universe. We are going to witness the alchemy of the gods. Prepare yourself. We are leaving the silence of the core. We are ascending back to the surface, but we are not alone. Another star is approaching. The gravity waves are beginning to ripple. The time for stillness is over. The time for the merger has come. In the vast theater of the cosmos, solitude is the norm. Stars are separated by light years of emptiness, living and dying in isolation. But gravity is a patient matchmaker. Sometimes massive stars are born in pairs, twin giants orbiting a common center of gravity. They live their lives together, burn their fuel together, and eventually die together. Imagine a binary system where both stars have exploded as supernovae and collapsed into neutron stars. Now, instead of two shining suns, we have two city-sized spheres of ultra-dense matter, dark and terrifying, locked in a gravitational embrace. This is the setup for the universe's greatest magic trick. It is a dance of death that will last for billions of years, but it ends in a fraction of a second. And the result of that ending is the gold ring on your finger. These two monsters do not just orbit, they plow through the fabric of space-time. Einstein taught us that heavy objects moving through space create ripples, like a boat moving through water. These ripples are called gravitational waves. They carry energy away from the system. As the neutron stars orbit, they radiate this energy, and the orbit shrinks. Inch by inch, meter by meter, they spiral closer together. For millions of years, this process is slow, almost imperceptible. But as the distance closes, the speed increases. The gravity becomes stronger. The waves become more powerful. It is a runaway process. By the time they are a few thousand kilometers apart, they are tearing through space at a significant fraction of the speed of light, whipping around each other hundreds of times per second. If you could hear the gravitational waves, and with instruments like LIGO we effectively can, you would hear a low hum rising in pitch, a chirp that screams up the scale until it vanishes into silence. That silence is the moment of contact. Hello again, fellow travelers of the dark. I am Theodore, the researcher. We are witnessing one of the rarest and most spectacular events in the universe, a kilonova. If you want to understand where the atoms in your jewelry and the rare earth metals in your smartphone actually came from, this is the story you have been waiting for. Please, if you value this journey, verify that you are subscribed to the channel. It helps us keep the lights on in the void. Now, watch the collision. The final milliseconds of the merger are a storm of tidal forces. As the stars get within touching distance, the gravity of each one begins to deform the other. These are not rigid billiard balls anymore. They are droplets of neutron fluid being stretched into teardrops. The crusts crack and shatter, releasing blinding flashes of gamma rays. Then they touch. The collision speed is relativistic, 1/3 the speed of light. When two objects with the density of an atomic nucleus slam into each other at that speed, physics goes into overdrive. A massive shockwave ripples through both stars, heating the matter to trillions of degrees. The cores merge. For a brief moment, a hypermassive neutron star is formed, a wobbling, chaotic object that is too heavy to exist. It spins wildly, trying to hold itself up against gravity with centrifugal force. But it is a losing battle. The mass is too great. Within milliseconds, the central object collapses. It vanishes behind an event horizon. A black hole is born. But not everything fell in. In the violence of the collision, a small fraction of the star's mass, perhaps 1%, which is still equal to thousands of Earths, was ejected. It was splashed out into space like water from a clapping hand. This material is hot, dense, and rich in neutrons. It is expanding outward at 30,000 kilometers per second. And this, right here, is the alchemy. This expanding cloud of neutron-rich debris is the factory. Inside this cloud, a process called rapid neutron capture, or the R process, is taking place. On Earth, nature builds elements slowly. In a normal star, protons are mashed together over millions of years to make helium, carbon, oxygen. It is a slow, methodical cooking. But to make heavy elements like gold, platinum, or uranium, you cannot use a slow cooker. You need a pressure cooker. You need violence. Heavy nuclei are unstable. They want to decay. To build them, you have to bombard a seed nucleus, like iron, with neutrons so fast that it doesn't have time to decay. You have to force feed it neutrons. Here is a neutron. Take another, and another, and another. The nucleus bloats up, becoming incredibly heavy, incredibly radioactive. Then it transforms. Some of the neutrons turn into protons to stabilize the mix, and suddenly you have a new element. You have skipped the line of the periodic table. In less than 1 second, this cloud of debris transforms from a soup of neutrons into a treasure chest. It manufactures gold. It manufactures platinum. It manufactures iodine, xenon, uranium, plutonium. The scale of this production is staggering. In a single neutron star merger, like the one detected in 2017, named G007, the amount of pure gold produced was estimated to be somewhere between 10 and 100 times the mass of the Earth. Let that sink in. A ball of solid gold, the size of the planet Jupiter, floating in space, expanding into the void. Along with it, mountains of platinum, oceans of silver. This is not a metaphor. This is literal. The universe is printing wealth on a scale that makes the global economy look like a single grain of sand. This expanding cloud, glowing with the radioactive heat of these newly forged elements, is what astronomers call a kilonova. It is 1,000 times brighter than a standard nova. It shines with a distinct reddish light, colored by the heavy metals absorbing the blue spectrum. It is a beacon that tells the universe, new matter has been created. Lie. Over the next few weeks and months, the cloud expands and cools. It mixes with the interstellar medium, the gas and dust that floats between the stars, the gold, the platinum, the uranium. They become dust. They drift through the galaxy like seeds in the wind. They travel for millions of years. They pass through nebulae. They get caught in the gravity of giant molecular clouds. And here is the connection. Here is the punchline of the cosmic joke. 4.5 billion years ago, a cloud of gas and dust began to collapse to form our solar system. That cloud was not pristine. It had been salted by the deaths of previous stars. It contained the debris of supernovae, yes, but it also contained the dust from ancient neutron star mergers that happened long before the sun was born. As the Earth formed, gravity pulled these heavy dust grains together. The gold sank into the molten rock. The platinum was folded into the crust. The uranium was locked into the mantle. Every atom of gold in the ring on your finger, every gram of gold in the vaults of Fort Knox, every speck of gold in the circuitry of your computer, every single atom of it, was once inside a neutron star. It was once part of that city-sized crystal lattice. It was once squeezed to 1 billion tons per teaspoon. It was liberated by a collision of unimaginable violence thrown across the galaxy, and eventually found its way into the rock that became your home. When you look at gold, you're not looking at a shiny yellow metal. You're looking at a fossil. You're looking at the shrapnel of a cosmic war. Its value does not come from its rarity on Earth. Its value comes from the impossibility of its creation. To make that ring, 2 stars had to die, turn into ghosts, dance for 1 billion years, and then destroy themselves in a suicide pact that shook the fabric of space-time. That is the price of the metal you wear. It is a price paid in time, gravity, and starlight. But the creation of elements is just one part of the story. The collision leaves something else behind. We mentioned the black hole. The merger of 2 neutron stars is one of the primary ways the universe creates low-mass black holes. It is a transition point. The matter that falls back, that fails to escape in the Kilonova cloud, crosses the line of no return. It takes its secrets with it. The equation of state, the quark soup, the strange matter, all of it is hidden forever behind the event horizon. But the act of creating the black hole is itself a spectacle. As the matter swirls into the newborn darkness, it forms an accretion disk, a ring of fire spinning at nearly the speed of light. This disk generates magnetic fields of apocalyptic strength. These fields twist and snap, launching jets of particles outward along the poles. These jets are the gamma-ray bursts, short, intense flashes of high-energy radiation that act like cosmic sniper shots. If a jet is pointed at Earth, we see a brilliant flash of gamma rays that lasts less than 2 seconds. These are the short gamma-ray bursts that puzzled astronomers for decades. We knew they were happening, but We didn't know what caused them. Now we know. They are the birth cries of black holes formed from neutron star mergers, a beam of death announcing the creation of a grave. If such a jet were to hit a planet nearby, say, within a few thousand light years, it could strip the atmosphere, destroy the ozone layer, and trigger a mass extinction. The universe is a dangerous place. The same event that creates the gold for your civilization could also wipe your civilization out. It is a duality that defines existence. Creation and destruction are two sides of the same coin. This realization that we are intimately connected to these violent events changes how we see the periodic table. It is not just a chart in a chemistry classroom. It is a genealogy. Hydrogen and helium are the children of the Big Bang. Carbon, nitrogen, and oxygen are the children of normal stars. Iron is the child of the supernova. But the heavyweights, the gold, the lead, the uranium, they are the children of the monsters. We are walking museums of cosmic history. Our bodies and our technologies are patchworks of different eras and different deaths. Let us step back and look at the binary system again before the crash. Think about the precision of it. These stars are clocks. As they spin, they emit beams of radio waves, pulsars. We will explore pulsars in depth in a later chapter, but in the context of a binary, they are tools. By timing the pulses of two neutron stars orbiting each other, we can measure gravity with infinite precision. We can test Einstein's theory of general relativity to the breaking point. And every single time, Einstein wins. The orbital decay, the spiraling in, happens exactly as his equations predicted 100 years ago. It is a testament to the power of the human mind. We can sit on a small rock, write down symbols on a piece of paper, and accurately predict the behavior of city-sized nuclear stars colliding 1 billion light-years away. That is a different kind of miracle. That is the miracle of understanding. But there is a mystery that remains. We have detected the waves. We have seen the light. We have found the gold. But we still do not know exactly what happens during the crash. The computer simulations are good, but they are not perfect. The physics is too complex. Magnetic fields, fluid dynamics, neutrino radiation, general relativity, all interacting in a millisecond. What happens to the magnetic fields? Do they amplify? Do they create a new structure? What happens to the strange matter if it exists? Does it infect the debris cloud? Could there be strangelets floating in the gold dust? These are the questions that drive the next generation of astronomers. We are building better detectors. We are building louder listeners. We want to hear the crash in high definition. As we drift away from the fading glow of the Kilonova, leaving the newborn black hole in the dark, we carry with us a piece of the truth. The universe is not a static place. It is a machine that recycles. It takes the dead and makes them useful. It takes the collapsed and makes them precious. It is a system of flow from gas to star to remnant to dust to planet to life. We are just a temporary arrangement of these recycled atoms. We are the universe observing itself, wearing the ashes of its own destruction as jewelry. So, the next time you hold a piece of gold, do not just see the shine. Feel the weight. Feel the density. That density is a memory. It is a memory of the crush. It is a memory of the neutron star. Close your eyes and and try to hear the chirp. Try to hear the scream of space-time as two ghosts collided to make that metal. It is the most expensive thing you will ever touch, not because of the price tag, but because of the cost of its creation. Now, we must turn our attention to another aspect of these stars. We have looked at their mass, their density, and their collisions. But there is a force we have mentioned only in passing, a force that deserves its own chapter of terror. Magnetism. We are about to enter the realm of the Magnetar. We are going to visit a star that can strip the information from your DNA from 1,000 kilometers away. We are going to see what happens when the magnetic field becomes stronger than the quantum limit. We have spoken of gravity. We have spoken of density. We have spoken of the crushing weight that turns mountains into millimeters. But there is another force in the universe, a force that is often quieter, often hidden, but which, in the right circumstances, can rise up to challenge even the power of a black hole. That force is magnetism. On Earth, we know magnetism as a gentle thing. It is the invisible hand that holds a drawing to your refrigerator. It is the needle of a compass pointing north, guiding ships across the ocean. It is the silent hum of an MRI machine peering inside your body with a field strength of perhaps 3 Tesla. We respect it, we use it, but we do not fear it. We do not look at a magnet and see a weapon of mass destruction. But that is because we live in a magnetic lullaby. We live in a universe where magnetism is usually a whisper. Today, we are going to visit the place where magnetism becomes a scream. We are going to visit the Magnetar. Imagine a star that does not just pull you in with gravity, but which reaches out with invisible fingers to unzip the very atoms of your body from a distance greater than the moon. Imagine a star where the magnetic field is so intense that the vacuum of empty space itself becomes solid, acting like a prism that splits light. Imagine a star where a storm is not wind or rain, but a rearrangement of the magnetic field lines that releases enough radiation to sterilize a solar system. This is not science fiction. This is the reality of a small subclass of neutron stars. About 1 in every 10 neutron stars is born with a secret. It is born spinning incredibly fast, and its internal fluids are churning in a way that generates a magnetic field 1,000 times stronger than a normal neutron star and a quadrillion times stronger than the Earth's. We call these monsters Magnetars, and they are, without a doubt, the most dangerous individual objects in the cosmos. Hello again. I am Theodore, the researcher. We are halfway through our journey into the dark heart of matter. We have survived the crush, the superfluid, and the collision. Now, we face the field. If you are enjoying this deep dive into the extremes of physics, and if you want to help us continue to bring these stories to light, please verify that you are subscribed. It is a simple act that keeps this channel alive. Thank you. Now, let us enter the magnetic storm. To understand the Magnetar, we have to talk about numbers that break the human mind. Let us use the unit of magnetic field strength called the Gauss. The Earth's magnetic field, the one that protects us from solar radiation and guides the birds, is about 0.5 Gauss. A strong refrigerator magnet is about 100 Gauss. A medical MRI machine which is strong enough to rip a steel chair out of your hands and throw it across the room, is about 30,000 to 50,000 Gauss. This is the limit of our daily experience. Now, look at a normal neutron star. Its field is around 1 trillion Gauss. That is 10 to the power of 12. That is already insane. But a magnetar? A magnetar sits at 10 to the power of 15 Gauss. 1 quadrillion Gauss. To put that in perspective, a magnetar is to a refrigerator magnet what a hydrogen bomb is to a firecracker. What does a field of that magnitude actually do? It does not just attract metal. It changes the shape of reality. Let us go back to the atom. We learned in school that atoms are mostly empty space, with a nucleus in the center and electron clouds orbiting around it. These clouds are roughly spherical. That shape is determined by the electric forces between the proton and the electron. But a magnetic field exerts a force on moving charges. It pushes them. In a weak field, the electron ignores it. In a strong field, the electron orbit gets nudged. In a magnetar's field, the magnetic force becomes stronger than the electric force holding the atom together. The sphere is destroyed. The electron cloud is crushed. The atom is squeezed into a thin, needle-like cylinder. It becomes a thread. This transformation, the spaghettification of atoms, changes all of chemistry. Chemistry depends on electrons sharing orbitals, locking together like Lego bricks. But if you turn the spherical bricks into needles, they cannot lock. Chemical bonds as we know them become impossible. Molecules break apart. Matter dissolves. If you were to approach a magnetar long before the gravity killed you, the magnetic field would destroy you. At a distance of 1,000 kilometers, roughly the distance from London to Berlin, the magnetic field would be strong enough to stop the bioelectrical impulses in your nerves. You would simply turn off. Your heart would stop. Your brain would cease to fire. You would die instantly, without pain, because the signal to feel pain could not travel to your brain. But if you drifted closer, the horror would begin. The water in your cells is diamagnetic. It is repelled by magnetic fields. The iron in your blood is paramagnetic. The conflicting forces would rip your tissues apart on a cellular level. And then, as you got within a few hundred kilometers, the atoms themselves would deform. Your body would vanish into a cloud of atomic needles, aligning with the field lines like iron filings on a piece of paper. You would become part of the star's aura, but the most terrifying aspect of a magnetar is not what it does to you, it is what it does to itself. Remember the crust? That solid 10 billion times stronger than steel lattice of iron? In a normal neutron star, the magnetic field is frozen into that crust. But in a magnetar, the field is moving. It is twisting. The interior of the star is a superfluid dynamo, spinning and churning, winding the magnetic field lines up like a rubber band. The field lines want to snap back, but the crust is holding them. The tension builds. The stress on the crust becomes unimaginable. It is a battle between the strongest material in the universe and the strongest force in the universe. Eventually, the force wins. The crust cracks. This is the giant flare. It is the ultimate version of the starquake we discussed earlier. But because the magnetic field is so much stronger, the energy release is magnified 1,000-fold. The crust shifts, the magnetic field lines snap and reconnect, and a blast of pure gamma radiation is launched into the universe. We have seen this happen. On December 27th, 2004, A wave of radiation washed over the solar system. It hit the satellites first, blinding their sensors. Then it hit the Earth. It slammed into the upper atmosphere, ionizing the air, causing it to expand. It altered the Earth's ionosphere so much that it disrupted radio communications for hours. This blast came from an object called SGR 1806-20. Here is the terrifying part. SGR 1806-20 is not our neighbor. It is not even close. It is located on the other side of the Milky Way galaxy, about 50,000 light-years away. Let that sink in. An object 50,000 light-years away, a distance so vast that light takes the entire history of human civilization multiplied by 10 to cross it, released a flash so bright that it physically affected our planet's atmosphere. In that 1/10 of a second, that single star released more energy than our sun has released in the last 250,000 years. If SGR 1806-20 had been located within 10 light-years of Earth, the distance to our nearest stellar neighbors, that flare would have been an extinction event. It would have stripped the ozone layer. It would have irradiated the surface. It would have been the end of us, and we would never have seen it coming. The radiation travels at the speed of light. One moment, the sky is blue. The next moment, the sky is on fire. Magnetars are the silent assassins of the galaxy, ticking time bombs that can go off at any moment. And yet, the strangeness goes even deeper. We have talked about matter, but what about empty space, the vacuum? We usually think of the vacuum as nothing, but quantum mechanics tells us that the vacuum is actually a seething foam of virtual particles. Electrons and positrons are constantly popping into existence, borrowing energy from the vacuum, and then annihilating each other and vanishing. They exist for such a short time that we cannot see them. They are virtual. But in the presence of a magnetar's field, something magical happens. The magnetic field is so strong that it grabs these virtual particles before they can vanish. It organizes them. It polarizes the vacuum. This phenomenon is called vacuum birefringence. It means that empty space itself starts to act like a crystal. If you shine a light beam through a crystal, the light can split into two rays, or its polarization can rotate. This is what happens near a magnetar. The vacuum becomes a lens. Light passing near the star is twisted and bent, not just by gravity, but by the magnetism of the empty space itself. The nothing becomes something. It has structure. It has optical properties. The magnetar is so powerful that it forces the ghost particles of the quantum vacuum to stand up and salute. It proves that there is no such thing as empty in our universe. Everything is filled with fields, and if you pump enough energy into them, the hidden texture of reality reveals itself. This leads us to a profound realization about our own existence. We rely on the stability of the physical constants. We rely on the fact that atoms are round, that chemistry works, that space is transparent. But a magnetar shows us that these rules are not absolute. They are conditional. They depend on the local environment. In the shadow of SGR 1806-20, chemistry is a forbidden art. In the grip of that field, biology is a physical impossibility. We exist in a Goldilocks zone, not just of temperature, but of field strength. We need gravity to be strong enough to hold us down, but not strong enough to crush us. We need magnetism to be strong enough to shield us, but not strong enough to unzip us. We are fragile creatures, balancing on a tightrope between the extremes. But there is beauty in this terror. The magnetic field stores energy. It is a battery. A magnetar glows in X-rays not because it is hot from the collapse, though it is, but because the magnetic field is slowly decaying. The field energy is being converted into heat. This keeps the star hot for much longer than a normal neutron star. It is a star powered by magnetism. It is a magnetic star in the truest sense. And eventually, the field will win the war against itself. It will decay. The magnetar will slow down. The crust will stop cracking. The star will fade into a normal neutron star, and then into a cold, dark cinder. The monster will go to sleep. But for those first few 10,000 years of its life, it is the king of the high-energy sky. Why do we study them? Why do we care about these magnetic nightmares? Because they are the only laboratories we have for physics beyond the standard model. We cannot build a machine on Earth that generates 10 Saturn 15 Gauss. We cannot squeeze atoms into needles in a lab. If we want to understand how matter behaves under these conditions, we have to look at magnetars. They are nature's particle accelerators. They test the limits of our equations. Every time a giant flare hits our detectors, we get a free data dump from the universe. We learn about the density of the crust. We learn about the speed of the magnetic reconnection. We learn about the viscosity of the superfluid. We are stealing secrets from the dragon while it sleeps. There is also a mystery about their origin. Why do some stars become magnetars and others do not? It seems to depend on the spin at birth. If the core of the dying star is spinning very fast, perhaps 1,000 times per second, when it collapses, it creates a dynamo effect. The fluids churn so violently that they amplify the magnetic field exponentially in the first few seconds of the neutron star's life. It is a birth defect, a consequence of being born too fast. The star spins itself into a magnetic frenzy, locking in the field that will define its destiny. It is a reminder that initial conditions matter. The way you are born determines the monster you become. As we pull back from the magnetar, stepping carefully out of the danger zone where atoms dissolve, we are left with a sense of awe. We are used to thinking of energy as fire, or light, or motion. But here, energy is a silent, invisible cage. It is a field that sits in the dark, waiting. It is static, yet capable of ultimate violence. It challenges our definition of power. True power is not always an explosion. Sometimes true power is a field so strong that it dictates the shape of the atoms themselves. We have now seen the density, the composition, the collision, and the magnetism. We have built a picture of a star that is a solid, liquid, superconducting magnetic city in space. But there is one more behavior that defines these objects. One more way they announce their presence to the cosmos. They do not just sit there. They spin. And they beam. They are the cosmic lighthouses that keep time better than any atomic clock on Earth. We are about to enter the world of the pulsar. We are going to learn how these dead stars became the metronomes of the galaxy, and how we use them to create a map to Earth for any aliens who might be listening. The silence of the magnetar is heavy, but the rhythm of the pulsar is hypnotic. Can you hear it? Tick, tick, tick. It is the sound of a dead star spinning. It is the sound of the universe's heart. And it is where we are going next. Imagine standing on the deck of a ship in the middle of a pitch-black ocean. The water is calm, the sky is clouded over, and the world is a void of absolute darkness. You are lost. There are no stars to guide you, no moon to light the waves. But then, on the horizon, you see it, a flash, brief, sharp, and silent. You wait. Exactly 1 second later, flash. You wait again. Exactly 1 second later, flash. It is a lighthouse. It is a promise of structure in the chaos. It tells you where the rocks are, where the land is, and most importantly, it tells you that time is passing with a steady rhythm. In the vast, silent ocean of the universe, we have found these lighthouses. They are not built of brick and stone. They are built of neutrons and gravity. They are the pulsars, and they are the most precise clocks in the cosmos, ticking away the seconds of eternity with a reliability that rivals the beating of an atomic heart. We have spent our journey looking at the matter of the neutron star, the crust, the core, the strange fluids. Now, we must look at its behavior. A neutron star is born spinning. When a massive star collapses, the conservation of angular momentum takes over. Think of an ice skater pulling her arms in to spin faster. The core of the star pulls its arms in from a radius of thousands of kilometers down to just 10 kilometers. The rotation speed skyrockets. The star that once rotated lazily once a month now spins hundreds of times per second. And, as we discussed in the last chapter, it carries a monstrous magnetic field with it. This is the engine of the pulsar. The magnetic poles of the star, the north and south poles of its magnet, are rarely aligned with the axis it spins around. They are tilted, just like Earth's magnetic poles are tilted relative to our geographic poles. As the star spins, these magnetic poles sweep through space like the beams of a lighthouse. But instead of light, these poles blast out beams of radio waves, X-rays and gamma rays. Charged particles are accelerated along the magnetic field lines, traveling at nearly the speed of light. When they shoot out from the poles, they emit a focused stream of radiation. This beam is continuous. It never stops. But because the star is spinning, the beam sweeps across the sky. If Earth happens to be in the path of that sweep, we see a pulse, blip. The beam hits our radio telescopes. Then the star rotates away and the signal vanishes. Then it rotates back, blip, over and over again. The star is not actually pulsing in size. It is rotating. But to us, it looks like a flashing light in the deep dark. I am Theodore, the researcher, and today we are listening to the rhythm of the cosmos. We are exploring how a discovery made by a graduate student changed our understanding of the universe, and how these spinning ghosts provided us with a map to the stars. If you find comfort in the precision of the universe, please verify that you are subscribed. Let us tune in to the frequency of the stars. The story of the pulsar is one of the great romances of modern astronomy. It takes us back to 1967, to a muddy field in Cambridge, England. A young graduate student named Jocelyn Bell Burnell was operating a new radio telescope, literally a field full of wires and poles that looked nothing like the giant dishes we use today. Her job was to study quasars, distant active galaxies. But as she analyzed the miles of paper charts produced by the telescope, Scrutinizing the squiggly lines of ink by hand, she noticed something odd. There was a bit of scruff. A tiny recurring signal that didn't look like a quasar and didn't look like interference from a passing car or a radio station. It was a pulse. It repeated exactly every 1.337 seconds. It was relentless. Blip, blip, blip. At first, the scientific community was skeptical. Stars do not blink that fast. Variable stars take hours or days to change brightness. A signal repeating every second seemed artificial. It seemed too precise to be natural. For a brief, exciting moment, the astronomers labeled the signal LGM-1. It stood for Little Green Men. They genuinely considered the possibility that they had intercepted a transmission from an alien civilization. Was this a beacon? A navigation signal? A message? It was a humbling thought. We were listening to the dark, and the dark was tapping back. But as Jocelyn Bell found more signals in different parts of the sky, some faster, some slower, the alien hypothesis collapsed. It was unlikely that 4 different alien civilizations were all transmitting similar Morse code signals from different directions. The answer had to be natural. It had to be physics. They had discovered the neutron star. Before 1967, neutron stars were just a theoretical idea, a mathematical doodle on a chalkboard. Jocelyn Bell proved they were real. She proved that the universe could create objects of such extreme density that they could spin once a second without flying apart. But once a second is actually slow for a pulsar. As we continued to listen, we found the true speed demons. We found the millisecond pulsars. These are stars that spin hundreds of times every single second. The fastest one known, PSR J7748 246 AD, spins at 716 times per second. Close your eyes and try to imagine a sphere the size of a city, millions of billions of tons of matter, rotating 716 times in the time it takes you to say 1. The surface of that star is moving at a quarter of the speed of light. The centrifugal force is immense, flattening the star into a pumpkin shape. Yet, the gravity is so strong that it holds it together. If you were standing on the equator of that star, the spin would try to fling you off, but the gravity would still crush you down. These millisecond pulsars are the recycled stars we hinted at earlier. They are old neutron stars that have been spun up. Imagine a neutron star in a binary system with a normal companion star. The neutron star is a vampire. Its gravity pulls gas off the companion. This gas spirals down onto the neutron star, crashing onto the surface. But because the gas is orbiting, it has angular momentum. It hits the neutron star at an angle, giving it a little kick of speed. Over millions of years, billions of tons of gas fall onto the star, spinning it faster and faster and faster. It is like spraying a water hose on a bicycle wheel. The wheel spins up. The old slow pulsar is rejuvenated. It becomes a millisecond pulsar, a screaming banshee of rotation that will spin for billions of years. Some of these vampires are so aggressive that they completely consume their companions, leaving nothing behind but the lonely, spinning predator. We call these the Black Widow pulsars. They kiss their partners to death. The precision of these objects is what makes them truly transcendental tools. A millisecond pulsar is a better clock than almost anything humans have ever built. They are so stable that if a pulsar arrives 1 microsecond late, we know something happened to the signal on its way to Earth. We can use them to detect gravitational waves, ripples in space that stretch the distance between the pulsar and us, delaying the signal. We can use them to test general relativity. But, perhaps most poetically, we can use them to say, we are here. In 1977, NASA launched the Voyager spacecraft. They are destined to leave the solar system and wander the galaxy forever. On board, there is a golden record, a phonograph record containing sounds and images of Earth. It is a message in a bottle for any future civilization that might find it. But how would an alien know where the bottle came from? Earth means nothing to a species from the Andromeda galaxy. Our star is just one of billions. We needed a universal address. We needed a map that did not depend on human language or human constellations. So, Carl Sagan and Frank Drake designed a map using pulsars. On the cover of the golden record, there is a starburst diagram. The center is the sun. Radiating out are lines of different lengths. Each line points to a specific pulsar. Written in binary code along the line is the rotation period of that pulsar. Because pulsars are unique, each one has its own specific fingerprint of rotation speed, and because they are slowing down at a predictable rate, an alien civilization could look at that map, identify the pulsars we referenced, and triangulate the exact position of our solar system. Not only that, by measuring how much the pulsars have slowed down since the record was launched, they could calculate exactly when the ship was launched. The pulsar map is a map of both space and time. It is the most enduring "You Are Here" sticker ever created. Long after the pyramids have crumbled to dust, long after the sun has expanded and swallowed the earth, that golden record will still be drifting in the silence, and the pulsar map will still point back to the graveyard where humanity once lived. It is a chilling and beautiful thought. We use the dead stars to mark the location of the living. But you do not need to be an alien to appreciate pulsars. You can listen to them right now. Radio astronomers often convert the radio signals into sound waves so our ears can process the data. It is a haunting experience. A slow pulsar sounds like a drum. Thump, thump, thump. It sounds like a heartbeat. A slightly faster pulsar sounds like a ticking clock. Tick, 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 tick. But the millisecond pulsars, they are spinning so fast that the individual beats blur together into a tone. They sound like a hum, a mosquito buzzing in the dark, a synthesized note held forever. When you listen to that sound, you are hearing the rotation of a city-sized atomic nucleus. You are hearing the physical reality of the universe's density. It is not music, but it is a song. It is the song of extreme physics. There is a tragedy in the life of a pulsar, however. They are machines that run on loss. The energy for the beams, the energy for the radiation, comes from the rotation itself. Every time the lighthouse sweeps, the star loses a tiny fraction of its energy. It slows down. The tick gets slightly longer. It is a slow death, taking tens of millions of years. Eventually, the star spins too slowly to generate the high voltages needed to create the beams. The mechanism fails. The lighthouse bulb burns out. The beams turn off. The pulsar crosses what astronomers call the death line. It is still there. It is still a neutron star. It is still hot and dense and terrifying. But it is silent. It becomes invisible to our radio telescopes. It joins the graveyard of the galaxy, the millions of unseen, dark neutron stars drifting through the void. We estimate that for every active pulsar we see, there are thousands of dead ones floating nearby. They are the silent majority. They are the ghosts that have stopped haunting. Occasionally, one might be reawakened by a new supply of gas, but most will drift in darkness until the end of time. It reminds us that visibility is a privilege. We see the loud ones, the bright ones, the active ones. But the bulk of the universe is hidden in the dark, existing without fanfare. Studying pulsars also gives us a tool to probe the interstellar medium, the empty space between stars. When the radio pulse travels through the galaxy, it has to pass through clouds of electrons, the thin plasma of deep space. These electrons slow down the lower frequency radio waves more than the high frequency ones. This is called dispersion. When the signal arrives at Earth, the high notes arrive before the low notes. It sounds like a descending whistle. Phew, phew, phew. By measuring this delay, we can count exactly how many electrons are floating in the empty space between us and the star. We can weigh the nothingness. We can map the invisible clouds of the Milky Way. The pulsar acts as a probe, illuminating the darkness as its signal cuts through the fog. There is one specific system that deserves mention, the double pulsar. Two neutron stars orbiting each other, and both of them are pulsars. This is the holy grail of relativity. We can watch one pulsar pass behind the other. We can see its signal get eclipsed by the magnetosphere of its partner. We can measure the Shapiro delay, the time delay caused by the gravity of the foreground star bending the space that the background signal has to travel through. It is a laboratory that allows us to test Einstein's theories with a precision of 0.05%, and the theory holds. The geometry of space-time is exactly as curved as Einstein said it would be. In a world of chaos, the mathematical perfection of these objects is a source of profound intellectual peace. As we conclude this chapter on the cosmic lighthouses, let us reflect on the utility of the useless. When Jocelyn Bell found that bit of scruff, it had no practical value. It was just a smudge on a chart. But that smudge led to the discovery of a new state of matter. It led to the most precise clocks in the universe. It led to the map that will guide aliens to our home. It led to the confirmation of gravitational waves. Science does not always know where it is going. It just follows the signal. It follows the blip in the dark. We have listened to the heartbeat of the star. We have seen its beams sweep the sky. But the neutron star has one more secret to reveal, a secret hidden not in its spin, or its magnetism, or its core, but in its very surface. The mountains, the gravity, the time dilation. What would it actually be like to stand there, to look up, to look down? In the next chapter, we will conduct the ultimate thought experiment. We will descend to the surface not as scientists, but as tourists. We will experience the time warp. We will understand why a minute on a neutron star is not a minute on Earth. We are going to mess with the flow of time itself. Time is a liar. We perceive it as a steady river flowing at the same speed for everyone, everywhere. A second is a second. A year is a year. We build our civilizations on the assumption that clocks in London tick at the same rate as clocks in Tokyo, and indeed they do. But this stability is an illusion caused by the weakness of our home planet. Earth is a featherweight. Its gravity is so gentle that it barely dents the fabric of space-time. But if you travel to the domain of the neutron star, the river of time hits a waterfall. Gravity does not just pull on matter, it pulls on time itself. It stretches the seconds until they snap. It creates a local reality where the present moment drags its feet, reluctant to become the past. Today, we are going to land on the surface of a neutron star and check our watches. We are going to experience the time warp, not as a special effect in a movie, but as a fundamental consequence of the curvature of the universe. We are going to stand in a place where looking at the horizon means seeing the back of your own head, and where climbing a mountain 1 millimeter high requires more energy than climbing Everest. Welcome back to the edge of the abyss. I am Theodore, the researcher. We are continuing our voyage into the most extreme environments the cosmos has to offer. If you want to keep exploring the boundaries of physics and philosophy with us, please take a moment to verify that you are subscribed to the channel. Your support allows us to keep asking these heavy questions. Thank you. Now let us synchronize our chronometers. To understand the surface of a neutron star, you have to discard your Euclidean geometry. You know, the geometry you learned in school, where the parallel lines never meet, and the angles of a triangle add up to 180 degrees. That geometry works in flat space. But around a neutron star, space is not flat. It is knotted. The mass of the star, 500,000 Earths compressed into a city, digs a deep well in the fabric of reality. As we descend toward the surface in our indestructible imaginary spacecraft, the first thing you notice is the gravitational lensing. The gravity is so strong that it bends light paths like a glass lens. On Earth, the horizon is a line where the sky meets the ground. On a neutron star, the horizon seems to lift up. The ground does not drop away. It curves upward like a bowl. Because the light from the back of the star is bent around to the front, you can see more than 50% of the surface at once. In fact, if the star is compact enough, you might see the entire surface spread out before you like a map. And if you looked straight ahead, perfectly level, you might see a ring of light, photons that have been trapped in orbit, circling the star forever. If you turned your head, you might catch a glimpse of the back of your own helmet, the image having circled the star and returned to you. It is a hall of mirrors built by gravity. When we finally touch down, we land on a surface that is smoother than any mirror ever polished by human hands. The gravity here is 100 billion times stronger than on Earth. This intense pull crushes any irregularity. There are no valleys. There are no jagged cliffs. The landscape is a perfect geometric sphere of iron crystal, but it is not perfectly flat. There are mountains, but they are not the mountains of Earth. A mountain on a neutron star is a bump in the crust, perhaps 5 millimeters high, less than 1/4 of an inch. To our eyes, it would look like a slight imperfection, a tiny ripple in the iron floor. But do not let the size fool you. To build a mountain 5 millimeters high against that crushing gravity takes an immense amount of energy. To climb it would be impossible for a biological being. If you were to trip and fall off this 5-millimeter mountain, you would hit the bottom moving at millions of miles per hour? No, the distance is too short. But the impact energy? The potential energy released by a 1-kilogram object falling 1 centimeter on a neutron star is equivalent to the energy of a stick of dynamite. These mountains are small, but they are dense concentrations of mass. They are pimples on the star that disrupt the perfect symmetry. And because the star spins so fast, these tiny mountains act like paddles in the ocean of space-time. As they spin, they churn the gravitational field, sending out in continuous gravitational waves, ripples that we are trying to detect with our most sensitive instruments on Earth. A 5-millimeter bump on a dead star 1,000 light-years away might be shaking the mirrors in our observatories right now. Now, look at your watch. On Earth, the second hand sweeps. Tick, tick, tick. Here, on your wrist, it looks normal. Your heart beats at a normal rhythm. Your thoughts flow at their usual speed. Everything in your local frame of reference feels fine. But if you looked up at a telescope orbiting far away, or if you could see a giant clock floating in deep space, you would see something terrifying. The clocks in space are running fast. They are spinning wildly. And if an observer in space looked down at you, they would see you moving in slow motion. You would be frozen in a jelly of time. This is gravitational time dilation. Einstein predicted it in his theory of general relativity. Mass tells space how to curve. Space tells matter how to move. And gravity tells time how to flow. The stronger the gravity, the slower time moves. On the surface of a neutron star, this effect is not subtle. Depending on the mass and size of the star, time might flow 20 to 30% slower than in deep space. If you spent 1 hour on the surface, an hour and 20 minutes might pass for your friends on the spaceship orbiting above. That does not sound like much compared to the movie Interstellar, where an hour equals 7 years. But in the world of physics, a 30% difference is catastrophic. It means that the physics of the surface is out of sync with the universe. It means that light itself has to pay a tax to escape. This brings us to the gravitational redshift. Imagine a photon of light trying to leave the surface. It is a packet of energy shooting upward at the speed of light. But gravity is pulling it back. It is like throwing a stone into the air. The stone slows down as it climbs. Light cannot slow down. It always travels at the speed of light. But it can lose energy. For a light wave, losing energy means its frequency drops. Its color changes. A photon that starts as a high-energy X-ray or a blue visible photon climbs out of the gravity well, fighting for every inch. By the time it reaches deep space, it is exhausted. Its wavelength has stretched. It has shifted toward the red end of the spectrum. This red shift is the fingerprint of gravity. It is how we measure the compactness of the star from Earth. We look at the spectral lines of the elements on the surface, the iron, the carbon, and we see that they are shifted. They are not where they are supposed to be. They have been dragged to the red by the sheer effort of escaping the star. The light we see is the survivors, the photons that paid the toll and made it out. Standing there, bathed in the red-shifted glow of the universe, you would feel a profound sense of isolation. You are deep in a well. The rest of the cosmos is up there, moving fast, aging fast. You are preserved in a gravitational amber. It raises a philosophical question. If time is relative, what is now? Is your now the same as the now of a person on Earth? The answer is no. There is no universal now. The universe is a patchwork of different times, different rates of flow, stitched together by gravity. The neutron star is a pocket of resistance, a place where the universe refuses to hurry. But the surface is not just a place of distorted time. It is a place of extreme temperature. We mentioned earlier that these stars are born in supernovae. They start their lives at temperatures of hundreds of billions of degrees. They cool down quickly by their standards. But even after 1,000,000 years, the surface is still burning at 1,000,000 degrees. To our eyes, if we could see the full spectrum, the star would not look red or yellow. It would glow with a ferocious, blinding, blue-white light, peaking in the X-ray spectrum. It is so hot that the atoms in the atmosphere are fully ionized, stripped of all electrons. It is a plasma ocean, and yet, compared to the core, this surface is freezing. The core is 100 times hotter. The crust acts as a blanket, insulating the hot interior. Heat flows outward, bubbling up through the iron lattice, finally radiating away into space. This cooling process is slow. A neutron star holds on to its heat, like a miser holds on to gold. It has very little surface area to radiate from. Remember, it is only the size of a city. A normal star like the Sun has a surface area billions of times larger, so the neutron star stays hot. It glows in the X-ray sky for millions of years, a fading ember that refuses to go out. Let us imagine for a moment the weather on this world. We talked about the magnetic storms, but what about the atmosphere itself? The carbon atmosphere is only a few centimeters thick, but because of the gravity, the density gradient is extreme. At the top of the atmosphere, it is a vacuum. A few centimeters down, it is as dense as liquid mercury. If there were winds, they would be flows of superheated plasma whipping around the star at thousands of kilometers per second, driven by the star's rotation and the magnetic field. But the strong gravity clamps everything down. The atmosphere is likely stratified, layers of heavy elements sinking to the bottom, lighter elements floating on top. If the star accretes matter from a companion, if it steals hydrogen gas, that hydrogen floats on top of the heavy iron crust. It forms a volatile ocean. As the hydrogen piles up, the pressure at the bottom of the layer increases. The temperature rises. Eventually, the hydrogen ignites. Nuclear fusion kicks in, but this is not the stable burning of a star. This is a bomb. The entire surface of the neutron star explodes in a thermonuclear flash. We call this an X-ray burst. For a few seconds, the star screams with the energy of 1,000 suns, burning the stolen hydrogen into helium in a flash fire that covers the entire globe. Then the fuel is gone. The fire dies. The ash settles, and the star begins to steal again, waiting for the next explosion. It is a cycle of greed and violent indigestion. Standing on the surface during an X-ray burst would be, well, fatal is not a strong enough word. You would be vaporized, ionized, and scattered as subatomic particles before your brain could register the flash. But safely observing from our thought experiment, We see the power of gravity to drive nuclear reactions. Gravity is the engine. It squeezes the fuel until it has no choice but to burn. It turns the surface into a nuclear reactor that runs without control rods. As we prepare to leave the surface, to climb back up the gravity well and return to the flat space of the comfortable cosmos, we have to fight the escape velocity. We mentioned it is 1/3 the speed of light. Think about what that means. To leave Earth, you need a rocket. To leave a neutron star, you practically need a transporter. A chemical rocket would not work. The fuel is too heavy. The moment you loaded the fuel onto the ship, the gravity would pull it down so hard that the ship would collapse. The rocket equation, the math that governs spaceflight, becomes a nightmare. You cannot carry enough fuel to lift the fuel. You are trapped. The only things that leave a neutron star are light, radiation, and the occasional jet of particles accelerated by magnetic fields. Matter that lands here stays here. It is the ultimate roach motel of the universe. Particles check in, but they do not check out. The atoms of the asteroids that fall, the gas from neighbors, the dust of space, they all become part of the crust. They add their mass to the monster, bringing it ever closer to the critical limit, where it collapses into a black hole. And that is the ultimate destiny of every neutron star. They are waiting. They are sitting in the dark, accumulating mass, cooling down, slowing down. They are the penultimate state of matter, one step away from oblivion. When we look at them, we are looking at the waiting room for the end of reality. But before we ascend, take one last look at the stars above. Because of the gravitational lensing, the sky looks different. The field of view is compressed. The constellations are distorted. The universe looks like it is wrapping around you. It is a view that no human eyes will ever see, but which physics allows us to see in our minds. It is beautiful, and it is claustrophobic. It is the view from inside the fist of God. Now, let us engage our imaginary engines and push away. We feel the time dilation easing. The universe speeds up. The light from the stars shifts back to its normal color. We are returning to the flow of time that we understand. We are leaving the island of slow time behind. But we carry the knowledge with us. We know that time is not absolute. We know that solid is a relative term. We know that the universe hides its most interesting physics in the most dangerous places. We have explored the star itself, but a neutron star does not exist in a vacuum, figuratively speaking. It interacts with its environment. It has companions. It has planets. Yes, planets. The very first planets ever discovered outside our solar system were not found around a normal star like the Sun. They were found orbiting a pulsar, a dead star with zombie planets. How can a planet survive a supernova? What is life like on a world bathed in X-rays and lashed by a pulsar beam? In the next chapter, we are going to visit these zombie worlds. We are going to walk on the diamond planets and the scorched earths that orbit the undead. The year was 1992. The world of astronomy was holding its collective breath. For decades, we had looked up at the stars and asked the most lonely question a species can ask: are we alone? We knew there were billions of suns out there, burning with the same fire as our own. Logic dictated that many of them should have planets. Logic dictated that some of those planets should be rocky, like Earth. But we had no proof. We had never seen a world outside our solar system. We assumed that when we finally found one, it would be orbiting a nice yellow star. A star like ours, a star capable of giving life. But the universe, as it so often does, decided to laugh at our assumptions. The first planets ever confirmed to exist outside our solar system were not found basking in the warmth of a living sun. They were found huddling around a corpse. They were found orbiting a pulsar named PSR B157 plus 12. It was a discovery that shocked the scientific community to its core. How could a planet survive a supernova? When a star explodes, it releases enough energy to vaporize everything in its vicinity. Any planets orbiting the original star should have been incinerated, blown into atoms, and scattered across the galaxy. And yet, there they were, 3 of them. 2 were roughly 4 times the mass of Earth, super-Earths, and 1 was a tiny world, barely more than the mass of our moon. They were real, they were solid, and they were orbiting a city-sized ball of neutrons that was blasting them with deadly radiation 160 times every second. These are the zombie worlds. They are the planets that rose from the dead. And today, we are going to walk on their surfaces. Hello again, my friends. I am Theodore, the researcher. We are nearing the end of our journey through the neutron star, but we cannot leave without visiting its children. If you are fascinated by the idea of worlds that should not exist, and if you want to support this archive of cosmic anomalies, please take a moment to verify that you are subscribed to the channel. It is a small gesture that helps us keep exploring the impossible. Thank you. Now, let us land on the world of the dead. The pulsar PSR B.57 plus 12 has been given a nickname, Lich. In fantasy folklore, a Lich is an undead sorcerer, a creature of great power that refuses to die. It is a fitting name. Its planets have been named Draugr, Poltergeist, and Phobator, names of ghosts and spirits from mythology. But these are not myths. They are rocks. How did they get there? The leading theory is that they are second-generation planets. They were not there when the star was alive. They formed after the death. After the supernova, a disk of debris, dust, gas, heavy metals, settled around the newborn neutron star. It was a disk of ashes. But gravity does not care if the material is fresh or recycled. Gravity just pulls. Over millions of years, the dust in this disk clumped together. It formed pebbles, then boulders, then planetesimals, and finally, planets. These worlds are made of the remains of the dead star. They are phoenix planets, born from the fire of their parents' destruction. Imagine standing on the surface of Poltergeist. It is a super-Earth, so the gravity is stronger than what you are used to. You would feel heavy, sluggish. The ground beneath your feet is likely rocky, perhaps rich in heavy metals forged in the supernova. But look up at the sky. There is no sun. There is no yellow disk crossing the heavens. Instead, in the center of the sky, there is a tiny, blindingly bright pinprick of blue-white light. It is thousands of times smaller than the sun in our sky, barely a dot, yet it is brilliant. But it is not a steady light. It is strobing. It is flashing 160 times per second. To the human eye, This might blur into a continuous, harsh glare, but to your instruments, it is a rapid-fire assault. The light is not warm. It is cold, hard X-rays and gamma rays. There is no heat to bask in, only radiation to hide from. And then there are the aurorae. The pulsar emits a wind of charged particles moving at relativistic speeds. This wind slams into the planet's magnetic field, if it has one, or directly into its atmosphere. On Earth, we get beautiful green and purple curtains of light near the poles when the solar wind hits us. On Poltergeist, the entire sky would be ablaze. Constant, violent, shifting curtains of neon light, dancing to the rhythm of the pulsar's magnetic sweep. It would be a psychedelic nightmare of color, a light show that never ends, illuminating a frozen, rocky wasteland. The radiation is so intense that if you stood there without protection, your DNA would be shredded in seconds. It is a sterile world, a world where life as we know it is impossible. And yet, it exists. It orbits. It keeps time. But Poltergeist is a rocky world. There is another type of pulsar planet that is even stranger. There is a planet orbiting the pulsar PSR J1719-1438. This planet is denser than platinum. It is roughly the mass of Jupiter, but it is less than half the size of Jupiter. It orbits its star so closely that a year lasts only 2 hours. If you were on this planet, you would celebrate a birthday every 120 minutes. What is this world? Astronomers believe it is the core of a white dwarf star that was eaten. The pulsar stripped away the outer layers of the white dwarf, the hydrogen, the helium, leaving only the dense, crystallized carbon core. Carbon, under extreme pressure, forms a crystal lattice. We have a word for crystallized carbon on Earth. We call it diamond. This planet is, quite literally, a diamond the size of a world. It is a single continuous crystal of carbon and oxygen, compressed to densities that make lead look like cotton candy. The diamond planet. It sounds like something from a fairy tale or a science fiction novel. But it is a deduction of rigorous physics. Standing on this world would be a visual experience beyond comprehension. The ground would be translucent, sparkling, refracting the harsh light of the pulsar into a billion rainbows. Light would travel deep into the planet's surface before being reflected back, making the ground glow from within. It would be a world of cold, hard luxury, a monument to pressure. But again, it is a dead world. The diamond is not a symbol of wealth here. It is a symbol of the crushing forces that stripped a star naked and left its skeleton to orbit a zombie. These worlds force us to rethink the definition of a solar system. We usually think of a solar system as a nursery, a place where life can grow. But the pulsar systems are graveyards. They are museums. They preserve the geometry of orbits long after the purpose of the orbit, to receive warmth and energy, is gone. They are mechanical systems, clockwork toys left running in an empty room. And the precision of these orbits is terrifying. Because the pulsar is such a perfect clock, we can detect the gravitational tug of these planets with incredible accuracy. We can measure the wobble of the neutron star caused by the planet's gravity down to a matter of meters. It is the most precise weighing scale in the universe. But is life truly impossible here? We scientists like to say impossible, but nature likes to say, watch this. Could there be life that does not rely on DNA? life that feeds on X-rays instead of visible light, life that lives underground, protected by kilometers of diamond or rock, using the geothermal heat of the planet's core. The planet is constantly being flexed by the pulsar's gravity. This tidal flexing creates heat. The core of the planet might be molten. There might be underground oceans. In the dark, warm depths of a pulsar planet, shielded from the deadly sky, could chemistry organize into biology? It is unlikely. The radiation environment is so hostile that complex molecules would be broken apart before they could build a cell. But we cannot say zero. The universe is vast, and our imagination is limited. Perhaps there are silicon-based forms or crystalline structures that live on the surface of the diamond world, feeding on the high-energy particles. We do not know. We likely never will. These worlds are thousands of light years away. We will never send a probe there. We can only look at the data, the wiggles in the radio signal, and dream. There is a tragic beauty to these systems. The pulsar, the neutron star, is slowly dying. It is spinning down. It is losing energy. The planets are huddled around a cooling ember. In a few billion years, the pulsar will cross the death line. It will stop beaming. It will go dark. And the planets? They will continue to orbit. Draugr, Poltergeist, Phobator. They will orbit a black invisible sphere in the eternal night. They will become true ghost worlds, unseen by anyone, tethered to a corpse that no longer speaks. They will drift through the galaxy forever, a silent family in the void. It is a lonely fate, but it is a fate that awaits all things. Even our own Earth, long after the sun dies, may end up as a frozen rock orbiting a white dwarf, drifting in the dark. The pulsar planets are just experiencing the future early. But sometimes the story is more violent. Not all planets survive. We have seen systems where the planet is being destroyed. The Black Widow pulsars we mentioned earlier often have companions that are being vaporized. The pulsar wind is so strong that it acts like a sandblaster. It strips the atmosphere off the planet. Then it strips the crust. Then the mantle. It ablates the planet layer by layer, turning it into a comet-like tail of gas that spirals into the neutron star. We are watching a star eat its children. It is a gruesome spectacle. The planet is screaming in radio waves as it dies, its material fueling the very beam that is killing it. It is a reminder that the neutron star is not a benevolent master. It is a monster. It commands its space with absolute authority. Anything that gets too close pays the price. Why do we study these zombie worlds? Because they teach us about the resilience of planet formation. They tell us that planets are robust. If nature can build planets in the hellish environment of a supernova remnant, then it can build planets anywhere. It implies that the universe is teeming with worlds. If the hardest place to build a planet still has planets, then the easy places, like around normal stars, must be overflowing with them. And indeed, since 1992, we have found over 5,000 planets around normal stars. But the pulsar planets were the first. They broke the dam. They opened our minds. They were the first proof that we are not unique. As we lift off from the surface of the diamond planet, leaving behind the sparkling plains and the strobe light sky, we carry a sense of perspective. We live on a paradise. Earth is a rare jewel not because of diamonds, but because of water, air, and magnetic shields. We are pampered by our sun. We are protected. The zombie worlds show us what the universe looks like when the protection is gone. They show us the raw, naked hostility of the cosmos. And yet, there is structure. There is order. Gravity still holds. Orbits still turn. The laws of physics do not abandon the dead. We have now explored the neutron star from every angle. We have seen its birth in fire. We have touched its crust of iron and its core of superfluid. We have witnessed the collision that makes gold. We have felt the magnetic storm and heard the ticking clock. We have walked on its planets. We have come to know this object intimately. But there is one final question, one final mystery that hangs over the neutron star like a shroud. What is the ultimate limit? A neutron star is matter fighting against gravity. The neutrons push out. Gravity pulls in. It is a stalemate. But every stalemate must end. What happens when gravity gets a little bit stronger? What happens when you add just one more teaspoon of matter to the star? There is a line in the sand, a mathematical limit known as the Tolman-Oppenheimer-Volkoff limit. It is the weight limit of the universe. If a neutron star crosses this line, the neutrons surrender. The strong nuclear force snaps. The star collapses. And what it becomes is no longer matter. It is a whole in reality. In the next chapter, we are going to approach this final boundary. We are going to watch a neutron star die its second death. We are going to witness the birth of a black hole. We are going to stand at the edge of the event horizon and ask, where did the matter go? And does the information of the star survive the fall? We are moving from the realm of the dense to the realm of the infinite. There is a rule in the universe that is absolute. It is a rule that governs bridges, buildings, bones, and stars. It is the rule of the breaking point. Every structure, no matter how strong, has a limit. You can stack bricks only so high before the bottom brick crumbles into dust. You can pull a steel cable only so hard before it snaps. Nature tolerates existence, but it does not tolerate infinity. For the neutron star, this rule is written in the language of quantum mechanics and general relativity. It is a line in the cosmic sand known as the Tolman-Oppenheimer-Volkoff limit. It is the weight limit of reality. And today, we are going to watch a star cross it. We are going to witness the moment when matter gives up the fight and vanishes from the universe, leaving behind only a scar in the fabric of space. We have spent this entire journey marveling at the strength of the neutron. We have seen how it holds up the sky against the crushing weight of 1 billion tons per teaspoon. We have called it the immovable object. But that was a lie. The neutron is not immovable. It is just stubborn. The strong nuclear force, the glue that holds the quarks together and keeps the neutrons rigid, is the strongest force in nature, yes. But gravity is relentless. Gravity is the only force that always adds up. The electric force can be shielded. Positive cancels negative. The strong force is short range. It only works inside the nucleus. But gravity reaches across the universe. It pulls on everything, and if you pile up enough mass, gravity becomes infinite. It becomes a god that refuses to be denied. Hello again, travelers of the void. I am Theodore, the researcher. We have reached the 9th chapter of our Odyssey. We are standing at the very edge of the map. Beyond this point, there be dragons. Beyond this point, Science turns into speculation, and matter turns into mathematics. If you are ready to face the ultimate darkness, please verify that you are subscribed to the channel. It is the only tether we have in the abyss. Now, let us watch the end of the world. Imagine a neutron star that is sitting right at the edge. It weighs perhaps 2.1 or 2.2 times the mass of the Sun. This is the danger zone. The neutrons in the core are screaming. They are packed so tightly that they are virtually overlapping. The pressure is unimaginable. The degenerate pressure, the quantum resistance that says two particles cannot occupy the same space, is the only thing holding the star up. The star is a dam holding back a flood of gravity. But this star is not alone. It has a companion, a bloated, red giant star orbiting nearby. The neutron star, with its intense gravity, is stripping gas from its neighbor. A stream of hydrogen and helium spirals down, crashing onto the surface. Day by day, year by year, the neutron star gets heavier. It adds a mountain of mass every second. The crust groans, the core compresses, the radius shrinks. The star is getting smaller and denser. It is tiptoeing toward the edge of the cliff. The Tolman-Oppenheimer-Volkoff limit, or TOV limit, is the specific mass where the quantum pressure can no longer withstand the gravity. We do not know the exact number because we do not know the exact equation of state for the core. Is it quarks? Is it hyperons? But we know it is there. It is likely around 2.2 to 2.5 solar masses. As the star accretes that final ton of gas, as that last asteroid falls onto the surface, the limit is breached. The dam breaks. The collapse is instantaneous. It happens faster than a neuron can fire in your brain. In less than a millisecond, the neutrons surrender. They are crushed. They do not just break into quarks. The quarks themselves are crushed. The geometry of space folds in on itself. The surface of the star, that hard, iron crystal landscape we walked on, falls inward at a significant fraction of the speed of light. But it does not hit a bottom. There is no bottom. The core has vanished. The star shrinks from 20 kilometers wide to 10 to 5 to 1 to 0. It becomes a singularity, a point of zero volume and infinite density. But we do not see the singularity. We see something else. As the star shrinks, its gravity becomes so intense that the escape velocity exceeds the speed of light. A shadow rises up to meet the collapsing surface. This is the event horizon. It is a spherical bubble of darkness that expands outward from the center, swallowing the star. One moment, there is a brilliant, glowing city of neutrons spinning in space. The next moment, pop, it is gone. It does not explode. There is no supernova. There is no flash of light. It is a unnova. The star simply winks out of existence. It is deleted from the observable universe. Where there was matter, there is now only a hole, a black hole. This transition from neutron star to black hole is the most profound transformation in physics. It is the destruction of structure. Think about what we lost. We lost the mountains. We lost the magnetic field lines. We lost the superfluid vortices. We lost the diamond planets. We lost the history of the star. A black hole has no mountains. It has no chemical composition. It has no surface to stand on. It has only three properties: mass, spin, and electric charge. That is it. This is called the no-hair theorem. A black hole has no hair. It has no details. It is a smooth, featureless object. All the complexity of the neutron star, the nuclear pasta, the iron lattice, the strange matter, has been erased, converted into pure geometry. It is the ultimate loss of information. It is the universe formatting the hard drive. Standing in space watching this happen, you would feel a wave pass through you. The collapse is violent. It shakes the fabric of space-time. The sudden disappearance of the star's volume and the formation of the event horizon sends out a burst of gravitational waves. We call this the ring down. It is like striking a bell. The black hole wobbles for a fraction of a second, radiating away the imperfections of the collapse, singing a tone that quickly fades into silence. Then it is quiet. The monster is sleeping. The gravity is still there. The planets of the system would continue to orbit the black hole, just as they orbited the neutron star. But the light is gone. The lighthouse has been extinguished. This boundary represents the failure of the strong nuclear force. We spend our lives thinking that matter is solid. We think that if we hit a wall, the wall stops us. That is the electromagnetic force. We think that atomic nuclei are indestructible. That is the strong force. But the black hole proves that these forces are not absolute. They are just temporary barriers. With enough gravity, you can crush the forces of nature. Gravity is the only thing that wins in the end. It is the patient conqueror. It waits for the fuel to run out. It waits for the structure to weaken. And then it claims everything. But let us dive a little deeper into the philosophy of this event. When the neutron star collapses, where does the matter go? Does it cease to exist? According to general relativity, it ends up in the singularity. But quantum mechanics hates that idea. Quantum mechanics says information cannot be destroyed. This is the black hole information paradox. If the intricate structure of the neutron star is truly erased, then physics is broken. Some theories suggest that the matter doesn't disappear. It is stored on the surface of the event horizon, encoded like a hologram. Others suggest that the singularity leads to a wormhole, a gateway to another universe, spewing the matter out as a white hole somewhere else. We do not know. The interior of a black hole is not science. It is destiny. It is a place where our timeline ends. However, there is a class of objects that might exist right on the razor's edge. We mentioned them briefly. Quark stars. If the neutrons break down into quarks, but the star doesn't collapse into a black hole, it might stabilize as a quark star. This object would be smaller than a neutron star, perhaps 10 kilometers across, and denser. It would not have a crust. It would be a naked sphere of quark soup, held together not just by gravity, but by the stickiness of the strong force itself. It would look like a giant metal ball, shimmering with a bizarre metallic liquid surface. If such a thing exists, it is the true final state of matter. But even a quark star has a limit. Add more mass, and even the quarks surrender. The black hole is inevitable. The formation of a black hole from a neutron star is also the source of some of the most violent signals we detect. Sometimes the collapse is not silent. If the neutron star is spinning incredibly fast when it collapses, the debris left behind forms a disk around the new black hole. This disk feeds the black hole, and the black hole spits out jets of energy. gamma ray bursts. These collapsars are engines of destruction. They drill a hole through the universe with a beam of radiation so intense it can be seen across the entire observable cosmos. It is the death scream of the neutron star, a final release of energy before the silence of the horizon takes over. This journey teaches us humility. We look at the ground beneath our feet and think it is permanent. We look at the mountains and think they are eternal. But the neutron star was billions of times harder than diamond, and even it was not permanent. Even it could not withstand the ultimate pressure. It reminds us that form is temporary. The universe builds structures, atoms, stars, people, galaxies, and then it destroys them. It is a cycle of construction and demolition. We are just lucky to be living in a quiet corner of the universe on a low-gravity rock where the forces of nature are balanced in our favor. We live in the habitable zone of density. Too little density and atoms don't form. Too much density and black holes form. We are the Goldilocks matter. But there is a strange comfort in the black hole. It is the ultimate safe. Nothing can hurt what is inside. It is cut off from the causal structure of the universe. It is a separate reality. Maybe the matter inside the neutron star, the star stuff that collapsed, is not destroyed. Maybe it is safe. Maybe it has transcended. In many religious and philosophical traditions, the shedding of the physical body is the path to enlightenment. The black hole is the physical realization of that concept. The body of the star is gone. The light is gone. Only the gravity, the influence, the soul remains. Let us rethink the timeline of the universe with this in mind. The universe began with the Big Bang, a singularity. It expanded, cooled, and formed particles. The particles formed stars. The stars died and formed neutron stars. The neutron stars merged and collapsed into black holes, singularities. We are moving from singularity to singularity. We are a brief interruption in the reign of the black holes. The era of starlight, the era we live in now, is just a fleeting moment. Eventually, in the deep future, all the stars will burn out, the galaxies will dissolve, and the universe will be populated only by black holes, drifting in the dark. The neutron stars that didn't collapse will eventually cool and fade, but the black holes will reign supreme for eons. They are the apex predators of the cosmos. So, when we study the TOV limit, we are studying the future. We are studying the mechanism by which the universe cleans up its mess. It sweeps the matter under the rug of the event horizon. It is a housekeeping measure. It ensures that gravity always has the final word. But before we succumb to the darkness, we must remember the light. The neutron star, before it collapsed, was a creator. It made the gold. It made the platinum. It acted as a lighthouse. It hosted planets. It lived a full life. Its death was necessary. Without the death of stars, we would not be here. Without the collapse, the universe would be boring. The violence is the price of complexity. We have stood on the surface. We have dived into the core. We have watched the collapse. Now, it is time to come home. It is time to return to Earth, to our soft, low-density bodies, and process what we have seen. In the final chapter, we are going to synthesize this journey. We are going to ask, why does this matter? Why should a human being living a short life on a small planet care about the density of a dead star? We are going to find the connection between the neutron star and the human soul. We're going to find the glory in the science. We will look at the night sky one last time, not as strangers, but as kin to the monsters in the dark. We are going to close the loop. We began this journey with a simple, almost trivial act. I asked you to look at your hand. I asked you to consider the emptiness inside your atoms, the vast, silent stadiums of space that separate your nuclei from your electrons. We used that emptiness as a counterpoint to the crushing reality of the neutron star, that city-sized jewel where the void has been squeezed out of existence. But now, at the end of our voyage, I want you to look at your hand again. Do not look at it as a collection of empty atoms this time. Look at it as a miracle of complexity. That hand contains carbon forged in the dying breaths of ordinary stars. It contains iron, created in the violent heart of a supernova collapse. It contains gold, a trace amount perhaps, but real gold, minted in the cataclysmic collision of two neutron stars, a Kilonova that happened billions of years before the Earth was born. Your hand is not just biology. It is a museum. It is an artifact. It is the final destination of a journey that began in the core of a sun and passed through the most hostile environments in the cosmos. We have spent 9 chapters looking out into the dark, staring at monsters. Now, we must look in. We must understand why we did this. Why does a species of soft, water-filled bipeds living on a rock that is barely a speck of dust in the galaxy care about the physics of dead stars? What is the point of knowing about nuclear pasta or superfluid vortices or the Tolman-Oppenheimer-Volkoff limit? Hello, for the final time in this series. I am Theodore, the researcher. We have reached the summit of our climb. We have stared into the abyss, and now we must find the meaning in what we saw. If this journey has shifted your perspective, if it has made the universe feel both larger and more intimate, please verify that you are subscribed to the channel. It is the best way to ensure that we can keep building these bridges between the human mind and the cosmic scale. Thank you for walking this path with me. Now, let us close the loop. The neutron star represents the other. It is the opposite of us in almost every way. We are warm. It is initially hot, but ultimately a cooling corpse. We are dynamic and changing. It is locked in a crystal lattice of near-eternal rigidity. We are fragile, held together by the tenuous electromagnetic bonds of chemistry. It is virtually indestructible, held together by the strong nuclear force and gravity. We are mostly empty space. It is the absence of space. By studying the neutron star, we define the boundaries of existence. We learn what matter can do, which helps us appreciate what matter does do in our case. The universe has a dial for density. Turn it all the way up, and you get a neutron star, a place where structure is crushed into uniformity, where individual atoms lose their identity, where the only thing that matters is the collective scream of the quantum fluid. Turn the dial down, and you get a nebula, a ghost of gas so thin it is barely there. But turn the dial to the precise, delicate middle setting, the Goldilocks density, and you get chemistry. You get biology. You get consciousness. You get you. We exist in the narrow window of possibility, where atoms can link hands to form molecules, where molecules can fold into proteins, and where proteins can dance together to create life. This complexity requires space. It requires the emptiness between the nucleus and the electron. That stadium of empty space we talked about in the first chapter, that is not wasted space. That is the stage where the drama of life happens. That is the room required for chemical bonds to flex and snap. The neutron star shows us what happens when you close the theater. The play ends. The actors are crushed. The music stops. So, when you think of the neutron star, do not just feel fear at its crushing power. Feel gratitude for your own emptiness. It is your low density that allows you to feel, to love, to think, and to wonder. We are the lucky ones. We are the matter that escaped the crush. But there is a deeper connection, a physical connection. We discussed the Kilonova, the merger of neutron stars. We discussed how these events forge the heavy elements of the periodic table. This is not just a trivia fact. This is the foundation of our technology and our physiology. The iodine in your thyroid gland, which regulates your metabolism and allows you to grow and think, was likely forged in a neutron star collision. Without neutron stars, the universe might be devoid of these heavy elements. Biology, as we know it, might not work. We are metabolically linked to these dead stars. The monsters in the dark are not just destroyers. They are the suppliers of the raw materials for complexity. The universe recycles everything. The death of a star is the birth of an element. The collision of the dead is the creation of the precious. We are walking around carrying the ashes of neutron stars in our bodies, using them to regulate our heat and our growth. We are not separate from the cosmos. We are continuous with it. The iron in the crust of the neutron star and the iron in your hemoglobin are brothers. They just took different paths. One was enslaved by gravity. The other was liberated by chemistry. And then there is the glory. I use this word carefully. I do not mean fame or religious worship. I mean the glory of the human intellect. Consider the improbability of what we have done here. We are primates. We evolved to find fruit in the jungle, to avoid predators on the savanna, to navigate the social hierarchies of a small tribe. Our brains are optimized for throwing rocks and recognizing faces. And yet, using these same brains, we have deduced the existence of a superfluid ocean inside a star 1,000 light years away. We have calculated the breaking point of the neutron. We have mapped the curvature of space-time. We have never been there. We will never go there. We cannot touch it, but we know it. We have built telescopes that act as extensions of our eyes, allowing us to see X-rays and hear radio waves. We have built mathematics that acts as an extension of our logic, allowing us to think in 11 dimensions. This is the triumph. The universe is vast, cold, and indifferent to us. It creates objects of terrifying power that could wipe us out in a microsecond without noticing. But we have a power too. We have the power to understand. We can hold the neutron star in our minds. We can model it. We can simulate it. We can predict its behavior. In a way, by understanding it, we contain it. The physical universe crushes us with its scale, but the mental universe encompasses it all. This is the Pascal's reed philosophy. Blaise Pascal said that man is but a reed, the most feeble thing in nature. but he is a thinking reed. The universe need not arm itself to crush him. A vapor, a drop of water, suffices to kill him. But if the universe were to crush him, man would still be more noble than that which killed him, because he knows that he dies, and the advantage which the universe has over him. The universe knows nothing of this. The neutron star does not know it is a neutron star. It does not know it is spinning. It does not know it is made of quarks. It just is. You are the one who knows. You are the universe's way of knowing itself. You are the consciousness of the cosmos. When you look at the simulation of a neutron star, it is the universe looking in a mirror. This realization transforms the feeling of insignificance into something else. Yes, physically, we are specks. If you stood on a neutron star, you would be a smear of atoms. But metaphysically, we are the giants. We are the meaning makers. The neutron star is just a pile of matter until a mind perceives it and calls it dense, beautiful, or terrifying. We bring the adjectives. We bring the wonder. Without us, or beings like us, the universe is just a silent movie playing to an empty theater. It is just blind forces interacting in the dark. We turn the lights on. We add the soundtrack. We give the story a plot. So, why does it matter what a neutron star is made of? It matters because the quest to find the answer drives us to the edge of our ability. It forces us to build better machines, invent new mathematics, and stretch our imaginations. It matters because it reveals the unity of physics. The same laws that govern the falling apple govern the collapsing star. But mostly, it matters because it is a challenge. The universe is hiding its secrets in the most dangerous places, inside the event horizon, inside the early universe, inside the neutron star core. It is daring us to come and find them. And we accepted the challenge. We did not stay in the caves. We did not stay on the ground. We looked up. We listened to the pulsars. We decoded the light. This journey is not just about science. It is about spirituality in its most secular and profound sense. It is about the feeling of awe. Awe is a complex emotion. It is a mix of fear and reverence. It is the feeling of being small in the presence of something vast, yet feeling connected to it. The neutron star is a generator of awe. When we visualize the sheer weight of it, 1 billion tons per teaspoon, we feel a vertigo of the soul. We feel the limits of our intuition breaking. This breaking is good for us. It shakes us out of our complacency. It reminds us that the world is not just taxes and traffic and social media arguments. The real world is strange. The real world is violent. The real world is made of quarks and space-time and gravity. Connecting with that reality is a form of meditation. It cleanses the doors of perception. It allows us to step out of our small, ego-driven lives and float for a moment in the deep time of the cosmos. I want you to imagine one last time that you are floating in space. But this time, do not look at the star. Look away. Look at the darkness between the stars. It looks empty. But you know now that it is not. You know it is filled with gravitational waves rippling from ancient collisions. You know it is filled with the faint radio pulses of dead stars ticking like clocks. You know it is filled with the dust of gold and platinum drifting toward new worlds. The darkness is alive with history. And then look at yourself. floating there, a tiny, fragile bubble of biology. You're the only thing in that entire vista that can say, I am. You're the only thing that can feel the cold. You're the only thing that can cry. That fragility is not a weakness. It is your crown. The neutron star gave up everything to become strong. It gave up its atoms, its chemistry, its space, its ability to change. It paid the ultimate price for stability. You kept your fragility, and in exchange, you got the universe. So, what is a neutron star made of? It is made of neutrons, yes. It is made of quarks, superfluid, and iron. It is made of gravity and time dilation. But in the end, for us, it is made of wonder. It is a canvas onto which we project our questions about the ultimate nature of reality. It is a mirror that reflects our own complexity by showing us the ultimate simplicity of the crush. As we end this series, I want to leave you with a charge. Do not let this knowledge sit in your brain as just a collection of facts. Do not just memorize that a teaspoon weighs 1 billion tons. Let that fact change you. Let it make you walk a little lighter on the earth. Let it make you look at your gold ring with a little more respect. Let it make you look at the night sky, not as a flat painting, but as a deep, three-dimensional ocean filled with monsters and miracles. The universe is not somewhere else. It is here. It is you. You are star stuff exploring star stuff. You are the way the universe feels its own heartbeat. We have traveled from the surface to the core, from the birth to the collapse, from the science to the soul. The story of the neutron star is the story of the limit, but the story of the human mind is that there are no limits. We will keep asking, we will keep looking, we will keep wondering, because that is what we are made of. We are made of curiosity. Thank you for joining me on this journey into the dark. It has been a privilege to be your guide. If you have felt the awe, if you have felt the connection, please leave a comment below. Tell me what you feel when you look up. Tell me which part of the journey resonated with you. And if you haven't already, subscribe and join our community of curious minds. We have many more journeys to take. The universe is infinite, and we have only just scratched the surface. Until next time, keep your feet on the ground, but keep your mind in the stars. I am Theodore, the researcher. And this has been the honest truth about the neutron star.